Starbucks serves millions of cups a day, but behind the scenes is a factory system so massive and tightly controlled, it turns raw beans into global consistency at an unbelievable scale. From sourcing and roasting to grinding, every step is timed to perfection to keep up with worldwide demand. In this documentary, we go inside the operation that fuels the most powerful coffee empires on the planet. The production of Starbucks products, particularly its packaged coffee offerings that end up in grocery stores, retail outlets, and international supply chains, begins long before a single bean is roasted. The entire process is built on one foundational element: green coffee sourcing. Starbucks, known for its commitment to quality and consistency, manages one of the most tightly controlled and globalized green coffee sourcing operations in the food and beverage industry. This first phase, the pre-roasting segment, is where the company sets the tone for every cup of coffee or bottled product it will eventually serve. And it's here we begin our highly detailed step-by-step journey. The green coffee sourcing process starts at origin in the tropical coffee-growing regions that straddle the equator, primarily Latin America, East Africa, and Southeast Asia. Starbucks primarily uses Arabica beans due to their more nuanced flavor profiles compared to the hardier but less complex Robusta variety. Within the Arabica family, beans are selected based on elevation, soil composition, rainfall, and harvest timing. Starbucks maintains long-standing relationships with coffee growers, cooperatives, and export mills in countries like Colombia, Ethiopia, Guatemala, Indonesia, Brazil, and Rwanda. But it's not as simple as ordering beans in bulk and having them shipped. Starbucks uses a proprietary set of sourcing standards known as Coffee and Farmer Equity Practices. These standards are not only a requirement for suppliers to be eligible, but also a multi-layered auditing framework. Cafe practices address 4 critical areas: product quality, social responsibility, environmental leadership, and economic transparency. Every farm or co-op that sells beans to Starbucks must pass rigorous inspections in these categories, many of which are carried out by third-party auditors trained in agricultural and labor practices. Once a farm or producer is approved under cafe practices, the beans are harvested, typically by hand. Hand-picking ensures that only ripe coffee cherries are selected, an essential factor in achieving flavor consistency in the final roast. These cherries are then processed at or near the farm using either the washed method. The washed method involves removing the pulp and fermenting the beans to eliminate the mucilage before drying, producing a cleaner, brighter flavor. The natural method dries the entire cherry and imparts a fruitier, heavier profile. The method used depends on the country, the farmer's infrastructure, and the target flavor profile desired by Starbucks blending teams. Once processed, the green beans are dried to a specific moisture content, usually between 10% and 12%, and stored in parchment until they are ready for export. Before leaving the origin country, the beans undergo a final hulling process to remove the parchment layer. At this stage, Starbucks' quality assurance teams at origin perform multiple assessments. These include physical evaluations and cupping, an industry-standard tasting method. Starbucks QA cuppers evaluate the green coffee on attributes like acidity, body, balance, sweetness, and aftertaste. Only those lots that meet Starbucks' sensory and structural requirements are approved for shipment. Approved beans are then packed into multi-layered jute bags with protective liners or into GrainPro plastic bags that guard against moisture and pests during transit. Each bag is tagged with a traceable barcode or lot number, which connects it to a digital database. This data includes not just the country and region of origin, but the exact farm or cooperative, harvest date, processing method, and quality score. This traceability is critical, not just for transparency and accountability, but also for quality replication year after year. Now begins the logistics phase. Starbucks contracts with specialized freight companies that understand the requirements of green coffee shipping. These beans are incredibly sensitive to temperature and humidity, even in raw form. A single exposure to high heat or excess moisture during transit can cause mold growth or flavor degradation. The beans are typically transported in temperature-stabilized shipping containers. If traveling by sea, the containers are outfitted with humidity control packs and dehumidifying systems. If air freight is used, the bags are carefully palletized, shrink-wrapped, and tagged with sensors that monitor environmental conditions throughout the journey. Upon arrival at one of Starbucks' roasting and manufacturing facilities, such as those located in York, Pennsylvania, Augusta, Georgia, Sandy Run, South Carolina, or Amsterdam, Netherlands, the green beans are unloaded, inspected, and entered into the factory's inventory management system. Before any production begins, each new shipment undergoes additional quality control. Samples from each bag or container are pulled and brought into the sensory lab. There, certified coffee graders perform cupping again, this time to ensure no quality loss occurred in transit. Moisture content, bean uniformity, and fragrance are retested. Beans that pass, these checks are tagged and routed to storage silos within the facility. These silos are food-grade, airtight steel vessels with internal climate regulation. Beans are stored based on variety, region, and intended blend. For example, Latin American beans destined for Starbucks blonde roast will be siloed separately from Ethiopian beans used in Starbucks Reserve offerings. Every silo is equipped with moisture sensors, thermometers, and pneumatic conveyor links, allowing operators to pull precise quantities for each roast batch according to master recipes. Before roasting can begin, beans are weighed into batches according to a specific ratio, depending on the blend being produced. Starbucks maintains an extensive library of proprietary blends, each with precise formulas. Some are single origin, where only one type of bean is used, while others, like Pike Place Roast or Espresso Roast, combine beans from multiple origins. Each blend is documented in the factory's recipe management software, which automatically calculates the needed amount of each component down to the gram and interfaces with weigh-scale systems to ensure accuracy. At this point, the beans are ready for roasting, but that process is highly intricate and deserves its own full analysis. Starbucks does not simply roast coffee by applying heat until the beans turn brown. The next step involves drum roasters, roast curves, heat profiling, airflow modulation, and real-time chemical transformation monitoring that will take the green coffee and convert it into the rich, aromatic, deeply flavored roasted beans that Starbucks is known for worldwide. With the green coffee beans now housed in precision-monitored silos and organized by blend formulation, the next phase of Starbucks' industrial production process transitions into what is often regarded as the heart of the entire operation: roasting. This stage is where the true transformation begins. The raw, pale green beans, earthy, grassy, and flavorless in their original state, are subjected to meticulously calibrated heat treatments that unlock their signature color, aroma, body, and complexity. Starbucks takes this phase extremely seriously, investing in proprietary roast profiles, customized equipment, and a multi-layered monitoring system to ensure that every batch matches the company's highly specific taste standards. The roasting process begins when a batch of green beans is called for from the storage silos. These silos are directly connected to the roasting equipment via stainless steel pneumatic transfer tubes. When an operator initiates a roast cycle, a preset quantity of beans, anywhere from 100 to 600 kilograms, depending on the size of the roaster, is discharged from the silo and transported through vacuum-sealed lines to the roaster's holding hopper. Here, the beans are pre-weighed on industrial platform scales connected to the plant's central production database, ensuring the exact quantity is delivered as dictated by the roast formula for that specific product, whether it's French roast, Pike Place, Sumatra, or espresso. Starbucks uses drum roasters for most of its large-scale production. These roasters consist of a rotating steel drum with an internal blade assembly that keeps the beans in constant motion. This ensures even exposure to heat as the drum is gradually raised to operating temperature, typically ranging between 190 degrees Celsius and 240 degrees Celsius, depending on the roast level. Lighter roasts, such as blonde roast, are roasted to lower final temperatures, while darker roasts, like French or Italian, require longer exposure and higher terminal heat. The roasting process follows a specific curve known as a roast profile. This is a data-driven graph that plots time against temperature, representing how heat is applied across the roast cycle. Starbucks profiles are proprietary and tightly controlled, with each product requiring a unique curve to deliver its intended flavor profile. These curves are not linear. They involve temperature ramps, plateaus, and even controlled dips. The initial drying phase lasts for several minutes, during which moisture is driven out of the bean. This is followed by the Maillard reaction phase, where sugars and amino acids begin to react, producing the rich brown coloration and the first wave of complex aromas. The most critical moment in roasting is known as first crack. This is when internal pressure in the bean causes it to physically crack open, producing an audible popping sound, much like popcorn. This marks a key transformation in bean chemistry. Starbucks roast operators listen for this moment, using audio sensors and thermal feedback to identify it precisely. Lighter roasts may be completed shortly after first crack, while medium and dark roasts continue through the development phase, where oils begin to emerge on the surface and flavor compounds deepen. Throughout this process, the roaster's control panel displays live data for bean temperature, exhaust temperature, airflow rate, and drum speed. The system is equipped with PID controllers and data logging software that feed into the factory's centralized SCADA system. Every roast is archived digitally, allowing Starbucks to recreate identical roast profiles across facilities on different continents, ensuring global consistency. Once the beans reach their designated roast level, they are immediately discharged from the drum into a cooling tray located below the roaster. This tray contains a rotating arm assembly that stirs the beans, while powerful fans blow ambient or chilled air upward from perforated grates below. Rapid cooling is essential to halt the roasting process and lock in the intended flavor and roast depth. If the beans are allowed to remain hot too long, they may bake, resulting in a flat, dull cup profile. The entire roasting to cooling process for a batch of coffee typically takes between 10 and 15 minutes, depending on the desired roast level and bean origin. Once cooled, the roasted beans are conveyed into degassing hoppers, stainless steel holding vessels, where the coffee rests for a short period, usually 12 to 24 hours. This rest period is necessary to allow CO2, a natural byproduct of roasting, to escape. If roasted beans are packaged too soon, the trapped gas can compromise packaging seals or even cause bags to inflate and rupture. However, some CO2 is desirable, especially for brewing freshness, so the timing of degassing must be carefully controlled. During this resting period, samples of each roast batch are collected and sent to the on-site sensory lab. Here, trained cupping teams evaluate the beans using controlled brewing and tasting protocols. They assess key attributes like aroma, acidity, balance, mouthfeel, finish, and overall quality compared to Starbucks' master profile for that roast. Cupping is performed blind and in duplicate to eliminate bias and ensure accuracy. If a batch falls outside of the acceptable range, it may be blended with other batches to correct the profile, used for internal consumption, or in rare cases, discarded. Once a roast batch passes quality inspection, it is routed towards the grinding and packaging area. Some products, like whole bean offerings, will skip the grinding stage entirely, while others destined for ground coffee bags or capsules will be milled using precision grinders. These machines are fitted with hardened steel burrs or rollers that crush the beans to an exact particle size distribution. Starbucks defines specific grind profiles depending on brewing method. For example, drip coffee grind is coarser than espresso grind, and French press is coarser still. Grinding is a highly sensitive operation. During the process, friction from the burrs generates heat, which can degrade volatile aromatics if not carefully controlled. To counter this, industrial grinders are equipped with chilled air systems and thermocouple sensors that regulate burr temperature and prevent overheating. In many facilities, grinding is conducted in a temperature-controlled room or during cooler hours of the day to preserve freshness. As soon as the coffee is ground, it moves to packaging, often through vacuum-sealed transfer tubes that prevent oxidation. The packaging stage is designed to preserve flavor and aroma while ensuring shelf stability. Starbucks uses multi-layer barrier films for its ground coffee products. These films include aluminum or metallized polyester layers that block oxygen and moisture. Many packages are fitted with one-way degassing valves that allow CO2 to escape without letting oxygen in, protecting the coffee's integrity while preventing package ballooning. Packaging machinery includes vertical form fill seal systems for smaller bags and horizontal form fill seal machines for pillow packs or multi-packs. Each package is filled to a specific weight, sealed and coded with production data, including roast date, location, shift, and lot number. High-speed check weighers and vision systems verify fill accuracy, seal integrity, and barcode clarity. Any package that fails inspection is automatically diverted off the line for rework. After packaging, the coffee products are grouped into cases and transferred to automated case packers and palletizers. Pallets are wrapped and labeled, then stored in temperature-controlled warehouses before shipping. These final steps, inventory control, cold chain monitoring, and outbound logistics, are critical to ensure the roasted Starbucks product reaches distribution centers and retail shelves around the world in optimal condition. With the coffee beans now expertly roasted, cooled, rested, and either packaged whole or ground and sealed, Starbucks' industrial production extends into another critical manufacturing domain, the preparation of its ready-to-drink beverages. These include bottled frappuccinos, chilled espresso drinks, cold brews, and dairy-based coffee blends. These products are not created in the same facilities that handle roasting and bagging. Instead, Starbucks partners with specialized beverage manufacturing facilities. Many cooperated with industry leaders like PepsiCo through the North American Coffee Partnership to manage this high-volume cold fill production. This stage involves liquid formulation, blending, thermal processing, homogenization, and sterile packaging under rigid food safety standards. The process begins with the formulation of the beverage base. For a bottled frappuccino, for example, this includes several core ingredients: brewed coffee extract, filtered water, sugar or corn syrup, dairy or dairy alternatives, stabilizers, and natural or artificial flavorings like vanilla, caramel, or mocha. Each component must be handled separately with precision before it's brought into the blending system. Coffee extract is typically delivered in concentrated form, produced by either brewing Starbucks beans at scale or using advanced extraction methods like cold concentrate percolation or high-pressure brewing. This extract arrives in refrigerated, food-grade totes or tanker trucks, depending on batch size. Upon arrival, it is sampled, analyzed for strength, and approved by the on-site quality control team before entering the liquid ingredient holding tanks. Simultaneously, dairy components such as milk and cream are received through chilled pipelines or aseptic bag-in-box systems. Dairy intake systems in Starbucks RTD plants are equipped with plate heat exchangers to quickly chill and store milk at temperatures below 4 degrees Celsius to maintain freshness and prevent bacterial growth. If using shelf-stable milk or UHT-treated dairy, the plant will still hold the product under cold storage until use. For plant-based SKUs, oat milk, almond milk, or soy milk are stored and handled in similar systems, albeit through dedicated lines to avoid allergen cross-contamination. Sweeteners and stabilizers such as sugar, corn syrup solids, carrageenan, cellulose gum, and pectin are weighed and pre-mixed in separate tanks. Starbucks beverages are engineered not just for taste, but for texture, mouthfeel, and visual consistency, especially in cream-based products like bottled mochas and vanilla frappuccinos. The stabilizers help suspend coffee solids, prevent dairy separation, and ensure the beverage maintains a smooth, homogeneous appearance on shelf, even after weeks or months in cold chain storage. All of these components, coffee extract, dairy or alternative milk, sweeteners, water, and flavor compounds, are brought together in the blending system. This usually consists of large stainless steel jacketed mixing tanks ranging from 1,000 to 5,000 litres. Each tank is equipped with an internal agitator, a bottom-mounted high-shear mixer, and in some cases, inline emulsifiers or homogenizers to ensure all elements are fully integrated. Tanks are fitted with load cells and flow meters, enabling automated dosing of each ingredient according to pre-programmed batch recipes. The blending system is monitored via a central control unit, typically a PLC-connected touchscreen interface that displays real-time values for temperature, mixing speed, pH, and ingredient flow. Operators can monitor the tank's temperature curve, the shear level during mixing, and the dwell time of each phase. In a typical Starbucks RTD batch, the blending cycle lasts between 30 and 60 minutes. During this time, inline sensors monitor turbidity, Brix, and viscosity. Samples are taken periodically to verify pH, flavor intensity, and microbial load before the batch is cleared for downstream processing. Once the beverage blend is complete and validated, the next stage is thermal processing. Most Starbucks RTD beverages are pasteurized using high-temperature, short-time systems, which allow for rapid heat treatment without compromising taste or texture. In HTST, the product is pumped through a heat exchanger that raises the liquid temperature to 85 degrees Celsius to 95 degrees Celsius for 15 to 30 seconds, then rapidly cools it to filling temperature, usually between 4 degrees Celsius and 10 degrees Celsius for cold fill lines, or slightly higher for hot fill bottles. This process effectively destroys any pathogenic microbes while preserving the coffee's aroma and flavor. Some facilities use ultra-high temperature processing for shelf-stable lines, allowing the product to remain unrefrigerated until opened. In UHT, the beverage is flash heated to temperatures up to 140 degrees Celsius for just a few seconds, then cooled quickly before packaging. The decision between HTST and UHT depends on the specific product's shelf life goals, packaging type, and distribution model. Immediately following thermal processing, the beverage passes through an inline homogenizer. This device applies intense pressure, often in excess of 2000 psi, to the liquid through a narrow valve, breaking down fat globules and suspended solids into microparticles. This step is critical for emulsion stability, preventing the cream from separating from the coffee or the flavor oils from rising to the surface. Homogenization also improves mouthfeel, making the beverage taste creamier and smoother. From here, the liquid is conveyed to the filling system. Starbucks RTD products are filled into a variety of package types: PET bottles, glass bottles, aluminum cans, and aseptic cartons. Each format requires its own dedicated filling and sealing system. For bottled frappuccinos, a cold fill rotary filler is typically used. This high-speed machine feeds sterilized bottles onto a rotating platform. where they are filled by gravity or volumetric fillers to exact fill levels. Immediately afterward, caps are applied, using steam-assisted capping heads to ensure a vacuum-tight seal and tamper resistance. Cans and cartons are filled on their respective lines, cartons often using form-fill-seal machines that shape the container, fill it, and seal the top in one continuous motion. All packages pass through automated detection systems that verify fill levels using weight sensors, check cap placement with vision systems, and scan barcodes to confirm packaging accuracy. Reject mechanisms immediately remove any container that fails these criteria. The filled beverages are then passed through a secondary cooling tunnel or refrigerated spiral conveyor that ensures they reach their final holding temperature before entering the packaging area. Depending on the product, this may be as low as 2 degrees Celsius, especially for refrigerated drinks destined for grocery and convenience store cold vaults. Once cooled, the individual containers are collected into multi-packs, shrink-wrapped, and placed into branded cartons. These cartons are then palletized by robotic arms and wrapped with plastic film. Each pallet is labeled with a unique identifier, linking it to the specific batch number, production date, filler line, and formulation ID. All of this information is uploaded into the factory's ERP system, providing full traceability from bean to bottle. Before any shipment is cleared, final product samples are pulled from each pallet for comprehensive testing. These include microbial testing, shelf stability stress tests, and sensory evaluations by trained panels. Only after all tests are passed are pallets released into refrigerated distribution channels for delivery to retail partners, Starbucks cafes, or direct-to-consumer platforms. From formulation and blending to pasteurization, homogenization, and ultra-clean packaging, this RTD production phase represents one of the most technologically advanced parts of Starbucks' global supply chain. It's where liquid meets logistics, combining industrial food science with tight controls over quality, taste, and branding. Every chilled bottle or can represents thousands of interconnected variables managed with absolute precision to deliver a consistent, enjoyable Starbucks experience anywhere in the world. With Starbucks ready-to-drink beverages now filled, sealed, chilled, and palletized, the focus shifts to the final, but no less complex, elements of factory operations. Sustainability integration, byproduct management, batch auditing, and outbound logistics. While the product may appear finished at this stage, the systems behind its release are still active, ensuring every bottle or can shipped reflects the brand's uncompromising quality, environmental responsibility, and traceability. One major component of this final phase is waste stream management. Every Starbucks beverage production facility is designed to minimize waste and make use of byproducts wherever possible. Coffee grounds remaining from extract production are collected and either sent to composting facilities, transformed into animal feed, or, in more advanced plants, used as biomass fuel to generate energy. Spent dairy materials or cleaning water are filtered and treated through on-site wastewater management systems, often returning grey water to municipal treatment plants within strict pH and chemical parameters. Packaging waste, including edge trims from shrink-wrap film, carton misprints, and PET bottle scrap, is separated and sent to in-factory compactors and balers. These bales are transported to certified recyclers for reprocessing. Starbucks has implemented programs at several manufacturing locations that convert unrecyclable soft plastics into composite shipping pallets or building materials, helping close the loop on production materials. In parallel with waste management, quality auditing continues even after packaging. Randomly selected finished products are pulled from every batch and routed to a dedicated quality assurance lab within the facility. There, they undergo another round of microbiological testing, sensory analysis, packaging integrity checks, and accelerated aging simulations. These simulations might involve storing the product at elevated temperatures for several days or weeks to mimic what could happen during prolonged distribution delays. Any deviation in flavor, appearance, or microbial safety can trigger a hold on the entire batch while root causes are investigated. All data generated, from roast date to filler head temperature, from pallet wrap tension to microbial test results, is logged in the facility's centralized manufacturing execution system. This digital record ensures that any shipment can be traced back through every step of the factory process. If a product recall is ever initiated, these logs allow immediate identification of affected units by date, location, and even by hour of production. When cleared, the finished pallets are scheduled for outbound logistics. Route planning software, inventory analytics, and order data from Starbucks' retail and grocery distribution teams are combined to determine where each batch will go. Products destined for grocery stores enter the cold chain system, transported in refrigerated trucks with temperature logs monitored in real time. Others, such as shelf-stable offerings, are routed to ambient storage hubs or export terminals for international shipping. The industrial production of condensed milk begins with the careful reception and preparation of raw cow's milk, a phase that determines the quality, efficiency, and final yield of the entire operation. As raw milk arrives at the condensed milk manufacturing facility, typically transported in insulated stainless steel tankers from contracted dairy farms, the first priority is immediate and rigorous quality assessment. Each truckload contains tens of thousands of litres of milk, and every batch must be verified to meet precise industrial standards before being accepted into the plant's supply chain. This initial phase involves a set of standardized protocols carried out in a dedicated receiving bay, equipped with specialized sampling and testing equipment. Upon arrival, the truck is docked to an unloading station, where automated lines connect directly to the tanker's valve. Before unloading can commence, operators perform a series of tests on a representative sample extracted from the tanker. This is done using a sanitized dipper or through a sample port using aseptic techniques to avoid contamination. The sample is then transferred to the plant's on-site quality control lab. Inside this lab, technicians first conduct a sensory inspection, evaluating the milk's color, smell, and presence of any visible particulates. While this step is basic, it's essential in immediately identifying any batches with gross spoilage or foreign contamination. The next series of tests are chemical and microbiological. A cryoscope is used to determine the freezing point of the milk, which helps identify dilution with water. Industrial condensed milk relies on unadulterated raw milk with tightly controlled fat and solids not fat contents. Any dilution affects the solids concentration required for the evaporation phase later on. Following this, infrared spectroscopy or mid-infrared analyzers are used to determine precise fat, protein, and lactose levels. These readings are compared against production targets, usually 3.5 to 4.0% fat and 8.5 to 9.0% SNF. If any component falls out of range, the milk may be either rejected or diverted to other dairy product lines. Another critical check is for microbial load. A rapid plate count, or ATP bioluminescence test, evaluates the total bacterial count per milliliter. Condensed milk production cannot start with high bacterial loads, as the concentration process would also concentrate any microbial byproducts, leading to off flavors and safety risks. Acceptable raw milk generally must have fewer than 100,000 colony-forming units per ml, with many plants enforcing even tighter limits. Additionally, presence of pathogens such as Listeria or Salmonella are monitored using immunoassay kits or PCR-based rapid tests. Antibiotic residue testing is also performed using either SNAP tests or microbial inhibition assays, since antibiotic contamination can disrupt the fermentation steps used in other dairy operations and might violate export regulations. If the sample passes all tests, the milk is cleared for unloading. The truck's contents are then pumped via sanitary stainless steel pipelines into raw milk holding tanks located within a temperature-controlled section of the facility. These tanks, typically ranging from 20,000 to 50,000 litres in capacity, are jacketed and agitated to maintain a constant temperature of around 4 degrees Celsius. At this stage, the milk is still unpasteurized and considered perishable, so time and temperature control are critical. The tanks are equipped with inline thermometers and CIP spray balls that will sanitize the internal surfaces between batches to prevent cross-contamination. The next step in the process is milk clarification and standardization. This is a pivotal moment where physical impurities and excess variability in composition are removed. The raw milk is fed from the storage tanks to a centrifugal clarifier, a high-speed rotating bowl separator that uses the density differences between milk solids and liquid to remove somatic cells, dirt, and other non-milk particles. The milk enters the spinning drum through a feed pipe, and under centrifugal force, heavier particles are flung outward against the bowl walls and discharged intermittently via sludge ejection ports. After clarification, the milk is sent to a cream separator. This piece of equipment operates similarly to the clarifier, but focuses on removing and isolating the cream layer from the skim milk portion. Depending on the desired end product specifications, some or all of the separated cream may be blended back in. This is where the standardization process comes into play. Condensed milk requires a tightly defined balance between fat content and total milk solids. Operators adjust this balance using inline blending systems, automated control loops equipped with flow meters and density sensors. The goal is to create a uniform milk base, typically around 8.5% fat and 22% total solids before it proceeds to pasteurization and evaporation. Any deviation at this stage would affect the efficiency of the next stages and could compromise the desired thickness, sweetness, and shelf life of the condensed milk. In more advanced factories, these composition adjustments are performed entirely by automated PLC systems. These use real-time data collected from inline sensors to control proportioning valves and regulate the mixing of cream and skim milk streams without any manual input. This level of automation not only ensures consistency, but reduces waste and energy use. The standardized milk is now homogeneous in composition, free of debris, and ready for thermal treatment. Before entering the pasteurizer, it may pass through a deaerator, a vacuum chamber that removes entrapped gases such as oxygen and carbon dioxide, which, if left in, could promote oxidation of fats and off flavors during storage. But up next is a step that changes the physical properties of the milk at a fundamental level. With the raw milk now cleaned, standardized, and compositionally balanced, it's time for it to undergo pasteurization and heat treatment, a step that prepares it for concentration without microbial risk or protein denaturation. This phase involves an intricate dance between temperature, pressure, and time, and it sets the stage for the transformative evaporation process that gives condensed milk its name. Now that the raw milk has been thoroughly received, clarified, and compositionally standardized, it is ready for thermal treatment. The next phase in the factory process is pasteurization, which is critical in destroying any pathogenic or spoilage microorganisms present in the milk. Pasteurization must be done with precise timing and temperature control to ensure microbial inactivation without damaging the milk's nutritional or functional properties, especially since this milk will soon undergo evaporation, which puts it under further thermal stress. To carry this out, the milk is directed from the holding tanks into a continuous flow, high-temperature, short-time pasteurization unit, which is the standard in industrial dairy processing. The HTST system typically consists of a series of plate heat exchangers that are engineered to raise the milk temperature to approximately 85 degrees Celsius for 15 to 20 seconds. This is hotter and slightly longer than conventional drinking milk pasteurization, as condensed milk requires greater microbial stability due to its extended shelf life. The process begins in the regeneration section of the plate heat exchanger, where incoming cold raw milk is preheated by outgoing pasteurized milk, allowing energy recovery and efficiency gains of up to 90%. The milk then moves through the heating section, where it is brought to the target temperature using hot water or steam circulated on the opposite side of the stainless steel plates. The timing of exposure is controlled by the flow rate and volume of the holding tubes, ensuring that every particle of milk receives uniform treatment. After pasteurization, the milk passes into a holding cell monitored by thermocouples and flow diversion valves. If the milk fails to reach or maintain the required pasteurization conditions, it is automatically diverted back to the raw milk tank for reprocessing. Once verified, the pasteurized milk is cooled again in the regeneration section, where it gives off its heat to the incoming raw milk, and then further chilled to around 60 degrees Celsius in preparation for the next crucial step, evaporation. Before entering the evaporator, the milk passes through a balance tank that helps maintain a constant feed rate into the evaporation system, stabilizing flow and avoiding temperature fluctuations that could cause burn-on or fouling inside the evaporator tubes. Now it's time to go into the evaporation stage, which is arguably the heart of the condensed milk production process. This is where the milk is physically transformed, thickened into a rich, viscous product through the removal of water. The goal here is to reduce the water content from its original 87% down to around 60%, achieving a final concentration of about 28% milk solids and 44% added sugar in the case of sweetened condensed milk. This is achieved through multi-effect vacuum evaporation, an energy-efficient process that allows for large-scale water removal without subjecting the milk to damaging high temperatures. The milk enters a multiple effect falling film evaporator, which is the industry standard for large volume dairy processing. In this system, the pasteurized milk is introduced at the top of vertical stainless steel tubes, where it forms a thin film as it flows downward. Simultaneously, steam is injected into adjacent chambers that surround the tubes, heating them indirectly. Because the evaporator is operated under vacuum, often at pressures around 70 to 100 millibar, the boiling point of the milk is reduced to around 55 degrees Celsius. This protects the sensitive proteins, sugars, and fats from heat-induced damage, preserving both flavor and nutritional quality. In a multi-effect setup, the vapor produced from one stage is used to heat the next stage, drastically improving energy efficiency. A typical 5-effect evaporator can remove over 85% of the water from milk with minimal energy input, thanks to this cascading reuse of thermal energy. The evaporated water is condensed and collected as waste heat condensate, which can later be recycled within the plant for cleaning processes or steam generation. Inside the evaporator, the thin film of milk continuously loses moisture as it falls. The combination of short residence time, low boiling point, and efficient heat transfer ensures that concentration occurs evenly and rapidly. By the time the milk reaches the bottom of the final effect, it has reached a viscous, concentrated state with a solid content of around 45%. At this point, it is discharged into an intermediate concentrate tank, where it is gently agitated and kept warm to prevent crystallization or skin formation on the surface. But the evaporation process alone does not fully define condensed milk as we know it, especially in the case of sweetened condensed milk. Once the desired solids concentration is achieved, the next critical step is the addition of sugar, which is not merely for taste, but serves as a functional preservative. The high sugar content lowers the water activity of the product to a point where microbial growth is virtually halted, granting it a long shelf life without refrigeration. The method of sugar addition must be extremely precise, as the wrong concentration can lead to issues like crystallization, viscosity problems, or even fermentation in rare cases. To do this, refined white sugar, typically sucrose, is added to the concentrated milk in the form of a hot sugar syrup. This syrup is prepared separately in jacketed mixing vessels, where dry granulated sugar is dissolved in water and heated to around 70 degrees Celsius. The syrup is filtered to remove any particulate matter and pumped into the concentrate tank under controlled flow rates. The typical formulation is around 46% sucrose by weight in the final product, which is determined by a combination of inline refractometers and density meters. The mixing of sugar syrup into the concentrate must be uniform to prevent localized crystallization and is often aided by low shear agitators that maintain homogeneity without introducing air. As the sugar is added, the milk becomes even more viscous and dense. At this point, the product's temperature is carefully maintained between 60 degrees Celsius and 65 degrees Celsius, as dropping below this range can initiate premature crystallization, while higher temperatures can scorch the milk solids. Once the sugar is fully integrated, the mixture is briefly held in a jacketed holding tank for a process known as equilibration, which allows any remaining air bubbles to rise and dissipate and gives time for the solution to reach equilibrium in terms of water activity and solute concentration. This marks the end of the thermal and compositional transformation stages. From a microbiological and physicochemical standpoint, the product is now shelf-stable, viscous, and chemically preserved by both heat treatment and high sugar concentration. However, it's not yet ready for packaging. There are still important steps to take involving cooling, crystallization control, and downstream finishing that are vital to achieving the smooth texture and glossy appearance that define high-quality condensed milk. With the concentrated sweetened milk now fully blended and equilibrated, the next critical phase in the condensed milk manufacturing process is controlled cooling and crystallization. This step is vital not only to achieving the desired texture and viscosity, but also to ensuring long-term product stability. If cooling is done too quickly or without proper control over nucleation, the lactose and sucrose in the product can crystallize into large, gritty particles. This not only affects mouthfeel, but can also lead to phase separation over time. To avoid this, the condensed milk is sent through a carefully engineered cooling and seeding system that promotes the formation of microcrystals, small, evenly distributed sugar crystals that give condensed milk its signature smooth, glossy consistency. The cooling system typically consists of scraped surface heat exchangers or jacketed tubular coolers. These systems are designed to handle highly viscous liquids and provide a high degree of thermal control. In scraped surface heat exchangers, the condensed milk flows through a cylindrical barrel while rotating blades constantly scrape the inner surface. This ensures that no product burns or sticks to the hot surface, and that the entire volume of milk is uniformly cooled. The cooling medium, usually chilled glycol or water, is circulated through the jacket, gradually lowering the milk temperature from around 65 degrees Celsius to 30-35 degrees Celsius. As the milk cools, it passes through a crystallization chamber where it is inoculated with fine lactose or sucrose seed crystals. These seed crystals are introduced in a controlled manner using a dosing system that meters out microscopic crystals with a high surface area. The goal is to initiate crystallization at a molecular level, encouraging the dissolved sugars to form consistent and extremely fine crystals rather than large, coarse ones. Agitators in the crystallization chamber are designed to promote gentle but thorough mixing, ensuring uniform distribution of the seed material without incorporating excess air. which could lead to oxidation or microbial contamination. Once seeded, the mixture is held at a stable crystallization temperature, typically around 30 degrees Celsius, for a period ranging from 30 to 90 minutes, depending on the batch size and product formulation. This resting period allows the crystals to grow slightly while remaining small and suspended, forming a delicate lattice within the viscous matrix of the milk. It is during this stage that the final texture of the condensed milk is locked in. Operators closely monitor the product's Brix value, viscosity, and temperature, using inline sensors and laboratory sampling to ensure that the crystallization proceeds according to specification. After the crystallization phase, the product enters the deaeration stage. Despite all precautions taken during processing, the condensed milk will inevitably contain some entrapped air, either from mechanical mixing, seeding, or agitation. This air must be removed before packaging to prevent oxidation, which can degrade both flavor and color over time. Deaeration also helps improve fill accuracy during packaging, ensuring a stable and uniform product weight in each container. Deaeration is typically carried out in a vacuum deaerator tank. The condensed milk is pumped into the tank, which is maintained under a vacuum of around -0.8 bars. Inside the tank, the milk is spread into a thin film across a series of rotating trays or falling film surfaces, maximizing the exposed surface area. As the product spreads out under vacuum, dissolved gases and trapped air are released and drawn out by the vacuum pump system. In some systems, nitrogen gas is also bubbled through the product as a stripping agent to help displace oxygen more effectively. This process is continuously monitored with oxygen sensors to ensure minimal residual oxygen levels in the final product, typically less than 0.5 milligrams per liter. Once deaerated, the condensed milk is often passed through a final homogenization stage. While not strictly required in all formulations, homogenization is frequently used to improve product consistency, prevent fat separation, and extend shelf stability. In this process, the milk is forced through a narrow orifice under high pressure, usually between 100 to 150 bar, causing the fat globules to break down into much smaller sizes, typically less than 1 micron in diameter. This prevents creaming or separation during storage and gives the final product a more uniform mouthfeel. The homogenizer used in this step is typically a two-stage piston-type homogenizer. In the first stage, pressure is applied to break apart the fat globules. In the second stage, the product is passed through an impact ring to further disperse and stabilize the emulsion. This ensures that the fat remains evenly distributed throughout the viscous condensed milk matrix, even after months of storage on a shelf. The process must be carefully balanced to avoid over-shearing the product, which could break the sugar crystal structure and lead to syneresis or texture issues. With the product now fully processed, it moves to the packaging line. Before any milk enters a can or a tube, the packaging material itself must undergo preparation. Metal cans are the most common format for condensed milk, though plastic tubes and laminated pouches are also used depending on market demands. The cans arrive at the factory either as pre-formed containers or as rolled flat blanks that are formed and sealed on site using can-forming machinery. If using pre-formed cans, the first step is depalletizing and feeding. The cans are automatically unloaded from shipping pallets and fed into a cleaning system via conveyor belts. Here, they pass through a high-pressure air blower system that removes dust and debris. They may also pass through an inverted rinse tunnel that sprays them with sterile water or a mild sanitizing solution. Optical sensors verify that each can is intact and free of damage before it proceeds. The clean cans are then transported to the filling station, where they are indexed into position beneath nozzles connected to a positive displacement filler system. These filling machines are designed to handle thick, viscous liquids with high precision. A typical condensed milk filling machine includes a volumetric dosing mechanism that ensures every can receives the exact same quantity, usually around 397 grams, the standard retail size. Sensors ensure the nozzles do not drip or splash, and the filling process is conducted in a low oxygen environment to prevent post-process contamination. As cans are filled, they immediately move to the vacuum closing station. This is another critical step in ensuring product longevity. Before the lid is sealed, a vacuum is applied to the headspace in the can to remove residual air. This helps prevent oxidation and maintains the slight negative pressure required for a tight seal. The lid is then applied and hermetically sealed using a double seam seaming machine. This creates an airtight seal by mechanically folding and compressing the lid and can flange together in 2 operations. The quality of this seal is checked automatically using seam gauges and vision inspection systems to detect any defects or incomplete closures. After sealing, the cans enter a hot water bath or steam chamber for thermal holding. This step, known as in-can sterilization or thermal stabilization, involves heating the sealed cans to around 85 to 90 degrees Celsius for 15 to 20 minutes. This serves several functions. It neutralizes any residual microbes that may have entered during filling, helps equalize pressure inside the can, and further reduces the water activity of the product. The heating process is tightly controlled using a time temperature data logger to ensure consistency across batches. Once the thermal holding is complete, the cans are rapidly cooled using chilled water sprays or immersion tunnels. This quick cooling halts the cooking process and helps set the product structure inside the can. It also prevents over-darkening, which can occur due to Maillard reactions between milk proteins and sugars at elevated temperatures. The cans are then dried using air knives and conveyed to the labeling and coding area. Each can is now labeled with full product information, including nutritional facts, production batch codes, expiration dates, and allergen warnings. Laser coders or inkjet printers apply traceability codes directly onto the lid or bottom of each can, allowing for full tracking throughout the supply chain. These codes are critical for food safety as they allow for rapid recall or identification of affected batches in the rare event of a contamination issue. From here, the cans are packed into cartons or shrink-wrapped into bundles using automated case packers. The cartons are stacked onto pallets and wrapped with stretch film for transport. At this stage, finished condensed milk is subjected to final quality inspection, where random samples from each batch are tested for Brix value, fat content, microbial load, viscosity, and packaging integrity. Once the batch is cleared, it is released for distribution. With the cans now fully sealed, labeled, and palletized, the condensed milk moves into the final stretch of its industrial journey: post-production storage, distribution, and market readiness. While it may seem that the heavy lifting is over, these concluding steps are far more complex and technologically managed than they first appear. Factories invest significant resources to ensure that every can of condensed milk not only leaves the facility in perfect condition, but also maintains its quality throughout the entire shelf life, often up to 2 years or more. Immediately after packaging, pallets of condensed milk are transferred to temperature-controlled finished goods warehouses. The climate in these storage areas is tightly regulated, typically kept between 15 degrees Celsius and 25 degrees Celsius, with relative humidity under 60%. This environment prevents moisture accumulation on the can surfaces and limits the rate of any chemical reactions inside the product, such as non-enzymatic browning. Even though the condensed milk is shelf-stable, excessive heat over time can darken the color and subtly change the flavor profile. These storage conditions are monitored 24/7 using IoT-connected environmental sensors that send real-time data to the facility's central control system. Each pallet is barcoded with batch numbers and entered into a digital warehouse management system. This system not only tracks location and inventory levels, but also enforces FIFO protocols to ensure older batches are distributed before newer ones. The traceability codes printed earlier on the cans come into play again here. Every single unit can be traced back to its raw milk intake, processing parameters, operator ID, and time-stamped process logs. This full chain traceability is a critical part of modern food safety compliance. When orders are received from retailers, exporters, or institutional buyers, automated robotic pallet pickers retrieve the relevant stock and move it to the outbound shipping area. Here, it is loaded into refrigerated or insulated trucks, depending on the destination and regional climatic conditions. In many cases, international shipments involve placing pallets into reefer containers that maintain stable temperatures for transoceanic shipping routes. Producing instant coffee in a factory is a complex process that combines food science, advanced engineering, and cutting-edge machinery to transform coffee beans into a soluble, ready-to-use product. From sourcing and roasting coffee beans to freeze-drying or spray-drying the brewed extract, each step in the production process is meticulously planned to ensure consistency, flavor preservation, and efficiency on a massive industrial scale. Let's take an in-depth look at the step-by-step factory process that goes into making instant coffee. The journey begins with sourcing green coffee beans. Factories procure these beans in large quantities from coffee-growing regions such as Brazil, Colombia, Vietnam, and Ethiopia. Since instant coffee requires consistent flavor profiles, manufacturers often blend beans from various regions to create a balanced and standardized flavor. Upon arrival at the factory, the green coffee beans are subjected to rigorous quality control checks. Samples are tested for size, moisture content, and defects to ensure the beans meet the factory's standards for processing. Once approved, the beans are stored in massive silos made of food-grade stainless steel or aluminum to protect them from contamination, pests, and humidity. These silos are equipped with automated systems that precisely dispense beans onto the production line. The first major step in processing the beans is cleaning. Coffee beans, even after being cleaned at their origin, may still contain impurities such as dirt, stones, sticks, or metal fragments. In the factory, the cleaning process involves several stages. Vibrating screens sift the beans to remove large debris, while air classifiers blow away lighter materials like husks or dust. Magnets are used to extract any metallic particles. Some factories also employ optical sorting machines, which use cameras and sensors to identify and remove defective beans or foreign objects. This thorough cleaning ensures that only high-quality beans proceed to the roasting stage. Roasting is a critical step in developing the rich, complex flavors of coffee. Factories use industrial coffee roasters, which can process thousands of pounds of beans per hour. The roasting process is controlled by highly advanced systems that allow operators to customize the roast profile for specific flavor outcomes. For instant coffee, medium to dark roasts are commonly used, as they bring out bold flavors that translate well into the final soluble product. Roasting temperatures typically range between 370 and 540 degrees Fahrenheit, depending on the desired flavor profile. During roasting, the beans undergo the Maillard reaction, a chemical process that creates the characteristic aromas and flavors of coffee. The roasting equipment includes temperature sensors and real-time monitoring systems to ensure uniform roasting across large batches. Once the roasting is complete, the beans are cooled rapidly to stop the roasting process and prevent overcooking. Factories use air cooling systems or water spray cooling, depending on the setup. Cooling is an important step, as improperly cooled beans can lose their flavor or become brittle. After cooling, the beans are sent to grinding machines. The grinding stage reduces the roasted coffee beans into smaller particles, which will be used for the brewing process. Factories use industrial grinders, such as roller mills or hammer mills, capable of producing a consistent grind size. The grind size is crucial because it affects the extraction process that follows. For instant coffee, a relatively coarse grind is typically used to optimize the brewing process in the factory. The ground coffee is then stored in intermediate holding bins, where it is kept fresh until it is ready to be brewed. Brewing is the next major step in instant coffee production, and it is carried out on an industrial scale. Massive brewing systems, similar to oversized percolators, are used to extract the soluble compounds from the ground coffee. These systems consist of large stainless steel extraction tanks or columns, which are designed to hold thousands of gallons of water and coffee grounds. Hot water is circulated through the coffee grounds at precise temperatures and pressures, mimicking the brewing process used at home, but on a much larger scale. Typically, water temperatures range between 190 and 205 degrees Fahrenheit, and the brewing time is carefully controlled to maximize flavor extraction while minimizing bitterness. The brewed coffee concentrate, a liquid containing the extracted soluble compounds, is then filtered to remove the spent coffee grounds. Factories use advanced filtration systems, such as centrifugal separators or fine mesh filters, to ensure that no solid particles remain in the liquid. The spent grounds are often dried and repurposed as fertilizer or biomass fuel, making use of every part of the raw material. At this stage, the coffee concentrate is a highly aromatic liquid, but it is still far from the final product. The challenge is to transform this liquid concentrate into a stable, dry, and soluble form. Factories use one of two main methods for this: spray drying or freeze drying. Spray drying is a fast and cost-effective method that is commonly used to produce instant coffee powder. The coffee concentrate is first preheated to reduce its moisture content. It is then pumped into a tall, spray drying chamber equipped with nozzles that disperse the liquid into fine droplets. At the same time, hot air, typically around 480 degrees Fahrenheit, is blown into the chamber. As the droplets fall through the chamber, the water in the coffee concentrate rapidly evaporates, leaving behind fine coffee powder. Spray drying is efficient and capable of processing large volumes, but the high temperatures can sometimes lead to a slight loss of flavor and aroma. Freeze drying, on the other hand, is a more delicate and sophisticated process that better preserves the natural flavors and aromas of coffee. The coffee concentrate is first frozen at extremely low temperatures, usually around 40 degrees Fahrenheit, to form solid slabs or granules. These frozen coffee pieces are then placed in a vacuum chamber. Inside the chamber, the frozen water in the coffee undergoes sublimation, a process where ice turns directly into vapor without passing through the liquid phase. This method requires precise control of temperature and pressure and takes longer than spray drying, but it produces high-quality granules of instant coffee that dissolve easily in water. After the drying process, the instant coffee is sifted and graded by particle size to ensure uniformity. Any oversized or undersized particles are removed, and the coffee is blended to create a consistent final product. Factories conduct rigorous quality control tests at this stage, including flavor analysis, solubility testing, and moisture content measurement. These tests ensure that the instant coffee meets the desired standards for flavor, aroma, and texture. Packaging is the final step in the production process, and it is designed to protect the coffee from moisture and preserve its freshness. The dried instant coffee is transported to high-speed filling machines, which dispense precise amounts of coffee into jars, tins, or pouches. Factories use nitrogen flushing systems to replace oxygen in the packaging, as oxygen can degrade the coffee over time. The jars are sealed with airtight lids, while pouches are heat sealed to maintain freshness. After sealing, the packages move to labeling stations, where automated systems apply branding, ingredient lists, and expiration dates. Each package undergoes a final inspection using vision systems to ensure there are no defects in the seals or labels. Once approved, the packages are packed into cartons or cases using robotic packing systems and prepared for shipping. Pallets of instant coffee are stacked and wrapped for stability before being loaded onto trucks or containers for global distribution. Throughout the entire process, factories rely on advanced automation and engineering to ensure efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems monitor and control every stage of production, from roasting and brewing to drying and packaging. Real-time data on temperature, pressure, humidity, and other parameters allows operators to make precise adjustments as needed, minimizing waste and ensuring high-quality output. Hygiene and food safety are also paramount in instant coffee production. Production areas are designed with food-grade stainless steel surfaces, seamless flooring, and clean room environments to prevent contamination. Positive air pressure systems are used to keep airborne particles out of critical areas, and employees are required to follow strict hygiene protocols, including wearing protective clothing and adhering to cleaning schedules. Factories are regularly inspected and certified to meet international food safety standards. Inside a tea factory, the transformation of fresh tea leaves into the familiar tea bags, loose leaf tea, or powdered varieties is a carefully orchestrated process. It is a seamless blend of tradition, precision engineering, and science. Every step of the way, from leaf intake to packaging, is designed to preserve the flavor, aroma, and quality that tea enthusiasts have come to expect. While the type of tea being produced, whether black, green, oolong, or white, dictates specific steps in the process, the overall journey is one of meticulous attention to detail, where both manual expertise and advanced machinery play vital roles. The process begins at the tea gardens, where leaves from the Camellia sinensis plant are plucked at peak quality. For most teas, workers handpick only the top 2 leaves and a bud from each branch, as these tender parts of the plant produce the best flavor and aroma. After harvesting, the leaves are transported to the factory as quickly as possible to prevent spoilage or fermentation during transit. Many tea factories are strategically located near plantations to minimize delays and ensure freshness. Upon arrival at the factory, the tea leaves are weighed and inspected for quality. Modern tea factories are equipped with automated intake systems that separate leaves from debris such as twigs or foreign matter. Vibrating conveyor belts or mechanical sieves are commonly used at this stage to remove unwanted materials. For higher grade teas, additional manual inspections may be carried out to ensure only the finest leaves proceed to the next step. The fresh leaves are then carefully spread out in thin layers on large trays or conveyor belts, marking the beginning of the first stage in tea processing. Withering. Withering is a critical step in tea production, as it reduces the moisture content of the fresh tea leaves and prepares them for the subsequent stages of processing. In the factory, withering is typically carried out in withering troughs, long, shallow trays equipped with a system of fans and controlled airflow. Fresh tea leaves are laid out on these trays, and air is circulated over them for several hours to slowly remove moisture. For black tea, withering may last anywhere from 12 to 18 hours, while green tea requires a shorter withering time, as it needs to retain more of its fresh, grassy flavor. Temperature and humidity are carefully controlled using automated climate systems to ensure consistent results. During this stage, the leaves become softer and more pliable, making them ready for rolling. The next stage is rolling, where the tea leaves are twisted and shaped to release their essential oils and initiate oxidation if required, as with black and oolong teas. Factories use large mechanical rolling machines equipped with heavy, grooved plates or rollers. These machines apply pressure to the leaves, breaking down their cell walls and releasing their natural juices. The released juices react with oxygen in the air, beginning the oxidation process that gives black tea its characteristic flavor and color. Rolling machines can be adjusted to produce different shapes and textures depending on the type of tea being made. For example, green teas may be rolled into tight pellets for varieties like gunpowder tea, while black teas are often left in long, wiry shapes. At this point, the production process diverges depending on the type of tea being manufactured. For black tea, oxidation is the next key step. Oxidation, often mistakenly referred to as fermentation, is a chemical process that darkens the tea leaves and develops the rich, robust flavors associated with black tea. In factories, oxidation typically takes place in large, temperature-controlled rooms, where rolled tea leaves are spread out on trays or conveyor belts. These rooms maintain a controlled environment with high humidity and a temperature of around 77 to 86 degrees Fahrenheit. The leaves are periodically monitored to ensure they achieve the desired level of oxidation, which can take anywhere from 30 minutes to several hours, depending on the tea. As the leaves oxidize, they turn from green to a reddish-brown color, releasing the aromatic compounds that define black tea. In contrast, for green tea production, oxidation is intentionally prevented. To preserve the vibrant green color and fresh vegetal flavor of the leaves, factories employ a process called fixation, also known as kill green. This step involves heating the leaves immediately after rolling to deactivate the enzymes that cause oxidation. Factories use either steam or dry heat for this purpose. For Japanese-style green teas, like sencha, the leaves are steamed in specialized machines, while Chinese-style green teas are often pan-fried in large heated woks or rotating drum roasters. Fixation requires precise temperature control, as overheating can burn the leaves and underheating can fail to stop oxidation completely. Once oxidation or fixation is complete, the next step is drying, which reduces the moisture content of the tea to make it shelf stable. Drying is typically carried out in large industrial dryers or ovens equipped with temperature controls and airflow systems. Conveyor belt dryers, in which the leaves are gradually moved through a heated chamber, are common in large-scale tea factories. The temperature during drying ranges from 194 to 248 degrees Fahrenheit, depending on the type of tea and the desired final moisture content, which is usually around 3 to 5%. This step is crucial for locking in the flavor and aroma of the tea while ensuring it will not spoil during storage. After drying, the tea leaves are sorted and graded. In the sorting process, leaves are separated by size, shape, and quality using a combination of vibrating sieves, air separators, and optical sorting machines. Whole leaves, broken leaves, and small particles are separated into different grades, which are used for various tea products. For instance, whole leaves are often reserved for premium loose-leaf teas, while smaller particles are used for tea bags. Some factories also employ advanced laser sorting machines that can detect and remove any remaining foreign objects or off-spec leaves. Blending is another key step in tea production, especially for brands that aim to create consistent flavor profiles. Many teas are blended by mixing leaves from different regions, harvests, or even types of tea. Blending is carried out in large rotating drums or mixing machines, where precise quantities of different teas are combined to achieve the desired flavor. For flavored teas, additional ingredients such as dried fruit pieces, herbs, or essential oils are added during this stage. For example, Earl Grey tea is made by blending black tea leaves with bergamot oil, while chai blends often include spices like cinnamon, cardamom, and cloves. Once the tea has been blended and sorted, it is ready for packaging. Packaging is a highly automated process in modern tea factories. For loose leaf tea, the leaves are weighed and sealed in airtight bags, tins, or foil-lined pouches to preserve freshness. For tea bags, the leaves are measured and packed into filter paper, which is then cut and sealed into individual tea bags using high-speed machines. Many factories also produce pyramid-shaped tea bags, which allow for larger leaves and better infusion. After filling, the tea bags are placed into cartons or boxes, which are sealed and labelled with branding, lot numbers, and expiration dates. Throughout the entire process, quality control plays a vital role in ensuring the tea meets rigorous standards. Factories employ trained tea tasters who sample the tea at various stages of production to assess its flavour, aroma, and appearance. Advanced laboratory equipment is also used to measure moisture content, microbial activity, and other parameters that affect the quality and safety of the final product. Additionally, factories must comply with food safety regulations and certifications, such as ISO 22000 or HACCP, to ensure their tea is safe for consumption. Cocoa powder, the cornerstone of countless recipes from rich chocolate cakes to creamy hot cocoa, is the product of a complex and fascinating manufacturing process that combines agricultural expertise with advanced industrial engineering. Behind every tin or packet of cocoa powder lies a detailed, multi-step operation where raw cacao beans are transformed into the fine, flavorful powder that has become a staple ingredient in kitchens around the world. This process begins on cacao farms and culminates in a factory where specialized equipment and precise techniques ensure the consistency, flavor, and quality of the finished product. Let's take an in-depth journey into how cocoa powder is made, exploring each stage of the process, from bean to powder. The story of cocoa powder begins with the cacao tree, which thrives in tropical regions near the equator, such as West Africa, Southeast Asia, and Central and South America. The cacao tree produces pods that contain cacao beans surrounded by a sweet, sticky pulp. These beans are the raw material for cocoa powder. Once harvested, the pods are split open to extract the beans, which are then immediately subjected to the first critical step in the process: fermentation. Fermentation is a natural and essential process that develops the flavor precursors in cacao beans. After being removed from the pods, the beans and their surrounding pulp are placed into shallow wooden boxes or large banana leaf-lined baskets, where they ferment over a period of 5 to 7 days. During this time, natural yeasts and bacteria break down the sugars in the pulp, generating heat and causing the temperature in the fermentation pile to rise significantly, often reaching over 120 degrees Fahrenheit. This heat triggers a series of chemical reactions within the beans, developing their characteristic chocolate flavor while reducing bitterness. The beans are turned periodically to ensure even fermentation and prevent spoilage. Once fermentation is complete, the beans are removed from the boxes or baskets and sent to the next stage: drying. Drying is critical for stabilizing the fermented beans and reducing their moisture content to a level suitable for storage and transport. Traditionally, cacao beans are dried under the sun, spread out in thin layers on large drying racks or patios, and turned regularly with wooden rakes to ensure even drying. In modern cocoa production, factories may use mechanical dryers when weather conditions are unsuitable for sun drying or to speed up the process. These machines blow heated air over the beans to achieve the target moisture content, which is usually around 6 to 7%. Proper drying is essential because any excess moisture could lead to mold growth during storage or shipping. Once dried, the beans are sorted, graded, and packed into jute bags or bulk containers, ready for shipment to processing facilities. Upon arriving at the cocoa processing factory, the dried cacao beans are carefully inspected for quality. Factories use advanced optical sorting machines equipped with cameras and lasers to identify and remove defective beans, such as those that are cracked, moldy, or undersized. Any remaining debris, like stones or twigs, is removed using vibrating screens and air separators. Once the beans are cleaned, they are stored in large silos made of food-grade stainless steel, which protects them from contamination while allowing for easy access as the beans move through the production line. The first step inside the factory is roasting, a critical stage that brings out the rich chocolatey aroma and flavor of the beans. Industrial roasters are designed to handle large volumes of cacao beans, roasting them at precise temperatures that can range from 250 to 300 degrees Fahrenheit. The exact temperature and duration of roasting depend on the type of cocoa powder being produced, as darker roasts develop more intense flavors, while lighter roasts preserve subtle fruity or floral notes. During roasting, the shells of the beans become brittle, and the internal nibs, which contain the cocoa solids and cocoa butter, begin to separate from the shell. Sensors and computer-controlled systems monitor the roasting process to ensure consistency across batches. Once roasting is complete, the beans are rapidly cooled, using air or water to prevent overcooking. The next stage is winnowing, where the roasted beans are cracked open to separate the nibs from the outer shells. This process is carried out using winnowing machines, which use a combination of mechanical rollers and air currents to break the shells and blow them away. The result is a pile of clean, roasted nibs, which are the purest form of cacao and the raw material for all cocoa products. The nibs are then ground into a thick, viscous liquid known as cocoa liquor, despite containing no alcohol. The grinding process involves heavy-duty industrial grinders, such as roller mills or stone grinders, which crush the nibs into tiny particles. This process releases the natural cocoa butter within the nibs, creating a smooth liquid that flows easily. The particle size is reduced to less than 30 microns during this stage to ensure a silky texture. Cocoa liquor is the base ingredient for many chocolate products, but for cocoa powder production, the focus shifts to separating the two main components of the liquor, cocoa solids and cocoa butter. The separation of cocoa solids and cocoa butter is achieved through pressing. Cocoa liquor is fed into hydraulic or screw presses, which apply immense pressure, up to 6,000 pounds per square inch, to squeeze out the cocoa butter. This process leaves behind a solid cake of compressed cocoa solids. The extracted cocoa butter is collected and filtered for use in other products, such as chocolate bars, cosmetics, or pharmaceuticals. Meanwhile, the cocoa cake, which still contains a small amount of residual fat, becomes the foundation for cocoa powder. The cocoa cake is cooled and broken into smaller chunks before being fed into pulverizing machines, where it is ground into a fine powder. Factories use various types of grinding equipment, such as pin mills or ball mills, to achieve the desired particle size for cocoa powder. This step is critical for ensuring that the final product has a consistent texture and dissolves easily in liquids. The fineness of cocoa powder can vary depending on its intended use. For example, baking-grade cocoa powder is typically ground finer than drinking cocoa. At this point, the cocoa powder is almost ready, but one additional process may take place depending on the type of cocoa being produced: alkalization, also known as Dutch processing. Alkalization involves treating the cocoa powder with an alkaline solution, such as potassium carbonate. This process neutralizes the natural acidity of the cocoa, darkens its color, and gives it a smoother, milder flavor. Alkalized cocoa powder is often used in baking and beverages, as its reduced acidity reacts differently with leavening agents like baking soda. Once the cocoa powder is fully processed, it undergoes rigorous quality control tests to ensure it meets the manufacturer's standards. Samples are tested for flavor, color, pH levels, fat content, and particle size. Factories use advanced laboratory equipment, such as spectrophotometers and viscometers, to measure these properties with precision. Any deviations from the desired specifications are identified and corrected before the product moves to the packaging stage. Packaging is the final step in the production process, and it plays a critical role in preserving the freshness and quality of the cocoa powder. The powder is first sifted to remove any clumps or oversized particles, ensuring a uniform texture. It is then transferred to automated filling machines, which dispense precise amounts of cocoa powder into containers such as tins, pouches, or bulk bags. For retail packaging, the containers are often flushed with nitrogen gas before sealing to remove oxygen and prevent spoilage. Labels are applied to the packages, including information such as the brand, product type, lot number, and expiration date. Once packaged, the cocoa powder undergoes a final round of inspections, where advanced vision systems check for defects such as improper sealing, misaligned labels, or damaged containers. The finished products are then packed into cartons or cases using robotic packaging systems. Palletizing robots stack the cartons neatly onto pallets, which are shrink-wrapped for stability and loaded onto trucks or shipping containers for distribution. The process begins with water, which forms the base of cherry Coca-Cola. It's not just any water that can be used. It must be highly purified to ensure no off-tastes or impurities interfere with the final product. Upon arrival at the factory, water undergoes a multi-step purification process. First, it is passed through large sand filters to remove visible debris and particulate matter. Next, it moves through activated carbon filters, which strip out chlorine and other organic compounds that could affect the drink's flavor. This step is crucial in ensuring a neutral tasting base. After this, reverse osmosis or microfiltration is employed to remove microscopic contaminants, bacteria, and dissolved minerals. This purified water is continuously tested for pH balance and purity before being approved for use. Now, it's time to introduce the sweeteners, which are responsible for cherry Coca-Cola's characteristic sweetness. The type of sweetener used depends on the region. In North America, high fructose corn syrup is the primary choice due to its affordability and efficient blending properties. In other regions, sucrose from sugarcane or sugar beets is used. HFCS is produced through an enzymatic conversion process that transforms cornstarch into glucose and then into fructose, creating a highly soluble and sweet liquid. The syrup, or sucrose, is delivered in tanker trucks and stored in large stainless steel silos within the factory. Before use, the sweetener is filtered and preheated to ensure it integrates seamlessly with the rest of the ingredients. The next essential ingredient is phosphoric acid, which gives cherry Coca-Cola its slight tang and acts as a preservative. Phosphoric acid is sourced from phosphate rock, which is treated with sulfuric acid to produce a food-grade acid that can be used in soft drinks. This ingredient arrives at the factory in concentrated liquid form and is stored in specialized tanks to prevent contamination. Precision is key when adding phosphoric acid. Even a slight variation in concentration can alter the drink's flavor balance, making it too tart or too flat. Caffeine, another critical component, is added to provide the beverage's stimulating effect. The caffeine used in cherry Coca-Cola is either extracted from coffee beans and tea leaves or synthesized in laboratories to maintain consistency. It arrives in powdered form and must be carefully measured before being dissolved into the syrup mixture. One of the most recognizable aspects of cherry Coca-Cola is its deep brown color, which is achieved using caramel color. Caramel color is made by heating sugar compounds with acids or alkalis, creating a complex mixture of caramelized sugars that provide both color and subtle bitter notes that complement the drink's sweetness. Caramel color must be carefully controlled for shade consistency, ensuring that every batch of cherry Coca-Cola has the same appearance. Now, it's time to add the proprietary natural flavors that define Coca-Cola's unmistakable taste. These flavors, known internally as Merchandise 7X, are a carefully guarded secret containing a mix of citrus oils, spices, and herbal extracts. The precise blend is known only to a handful of people within the Coca-Cola company. These concentrated flavoring agents are added in precise amounts, ensuring the signature cola taste remains identical across all global production sites. But what truly differentiates cherry Coca-Cola from its classic counterpart is the cherry flavoring. This is created using natural cherry extracts or synthetic cherry compounds, depending on local regulations and supply chain availability. Natural cherry extracts are obtained through cold pressing ripe cherries to capture their essence, while synthetic cherry flavors replicate the fruity, slightly tart taste using chemical compounds such as benzaldehyde. The cherry flavor must be added in a carefully measured amount to create a perfect balance with the cola notes without overpowering them. Once all the ingredients have been sourced, purified, and prepared, it's time for the next step: creating the concentrated syrup. In a dedicated syrup production area of the factory, large stainless steel mixing tanks equipped with powerful agitators are used to blend the ingredients into a homogeneous mixture. The process starts by heating the purified water slightly to improve ingredient solubility. The sweetener, whether HFCS or sucrose, is then gradually introduced while the mixture is stirred continuously to prevent crystallization. Next, the phosphoric acid is added, providing cherry Coca-Cola with its signature tangy undertone. Because phosphoric acid is highly concentrated, automated dosing systems are used to ensure precise measurement, preventing any deviations in taste. Following this, the caffeine is dissolved in a small amount of warm water before being incorporated into the syrup, ensuring even distribution throughout the mixture. The natural flavors, including the Merchandise 7X blend and cherry flavoring, are then carefully added. These flavor components are typically pre-mixed into an emulsified solution to ensure they disperse evenly throughout the syrup. This step is crucial, as any inconsistencies in flavor distribution can lead to variations in taste between different production batches. Finally, the caramel color is introduced, giving cherry Coca-Cola its signature appearance. Once all the ingredients are combined, the syrup undergoes a multi-stage filtration process to remove any undissolved particles. This is typically done using fine mesh filters or centrifugal separation methods, ensuring that the syrup is smooth and free from any impurities. After filtration, the syrup is transferred to holding tanks, where it is kept under controlled conditions before being sent to the bottling stage. Throughout the syrup production process, quality control plays a vital role. Factory workers take samples from each batch and conduct tests to measure sweetness levels, acidity, and overall flavor consistency. Sensory panels, trained employees who specialize in taste testing, evaluate the syrup to ensure it matches the established cherry Coca-Cola flavor profile. If any discrepancies are detected, adjustments are made before the syrup is approved for bottling. With the syrup now fully prepared, the next step is dilution, carbonation, and bottling. This is where the concentrated syrup is combined with carbonated water and packaged into cans and bottles for distribution worldwide. But before we get to that, the syrup must first be transported to the filling stations in a highly controlled manner. The next phase of production ensures that the correct syrup-to-water ratio is maintained and that the carbonation process delivers the signature effervescence that makes cherry Coca-Cola such a refreshing drink. Now that the syrup is ready, it's time to move on to the next critical stage: blending the syrup with carbonated water and ensuring that the correct levels of fizziness, taste, and consistency are achieved in every bottle and can. This process is where cherry Coca-Cola transforms from a concentrated mixture into the refreshing, bubbly beverage that millions of consumers enjoy. Now that the concentrated cherry Coca-Cola syrup is fully prepared and stored under controlled conditions, it's time to move on to the next crucial step in the manufacturing process: blending the syrup with carbonated water and ensuring the perfect level of fizziness. This stage is where cherry Coca-Cola takes its final form, transforming from a concentrated mixture into the refreshing, bubbly beverage that millions of people enjoy. The precision involved in this step is critical because even slight inconsistencies in carbonation or syrup dilution can result in an off-tasting product. The process begins with the careful transportation of the concentrated syrup to the filling stations. To prevent contamination and maintain consistency, the syrup is pumped through stainless steel pipes from the storage tanks to a specialized mixing unit known as a proportioner. The proportioner is one of the most vital machines in the entire production line, as it precisely controls the ratio of syrup to water. Cherry Coca-Cola's signature taste depends on the exact balance of ingredients, and any deviation in the syrup to water ratio could result in an overly sweet or weak-tasting beverage. The standard ratio for Coca-Cola products is approximately 1 part syrup to 5 parts carbonated water, but this can vary slightly depending on factors such as temperature and altitude, which can affect carbonation retention. Before the syrup and water are combined, the water must undergo a final round of purification to ensure absolute consistency. Even though the water has already been filtered and purified at the beginning of the process, additional treatment steps are performed just before carbonation. The water is passed through activated carbon filters once more to remove any remaining traces of chlorine or organic matter. Then it is chilled to a precise temperature, usually around 1 to 3 degrees Celsius. Chilling the water at this stage is essential because cold liquid absorbs carbon dioxide more efficiently, which results in finer and longer-lasting bubbles in the final product. Now comes the most intricate step: carbonation. The carbonation process is what gives cherry Coca-Cola its signature fizz and enhances the overall drinking experience. Carbon dioxide gas is injected into the chilled water under high pressure using specialized carbonation tanks. These tanks are equipped with fine diffusion plates that allow the gas to dissolve evenly into the liquid, ensuring consistent carbonation levels throughout the entire batch. The CO2 used in this process must be of food-grade quality, free from impurities that could alter the beverage's taste. To maintain the ideal carbonation level, the process is carefully controlled using high-precision sensors that monitor temperature, pressure, and CO2 concentration in real time. Once the water is fully carbonated, it is immediately mixed with the concentrated cherry Coca-Cola syrup inside the proportioner. This must be done swiftly to prevent any loss of carbonation. The high-speed blending process ensures that the syrup and carbonated water mix thoroughly without causing excessive foaming, which could lead to product loss. As soon as the mixture is complete, the freshly carbonated cherry Coca-Cola is sent directly to the filling lines for packaging. However, this must be done under strictly controlled conditions to maintain carbonation and prevent oxidation, which could negatively affect the beverage's taste and shelf life. The next step is the bottling and canning process, where the freshly mixed cherry Coca-Cola is transferred into its final packaging. This stage of production requires highly specialized machinery that can fill thousands of bottles and cans per minute while maintaining product integrity. The bottling and canning lines operate at incredible speeds, and every detail, from the fill level to the sealing process, must be executed with extreme precision. The filling process begins with the preparation of the containers. Whether the product is being packaged in aluminum cans, plastic PET bottles, or glass bottles, each type of packaging undergoes a thorough cleaning and sterilization process before being filled. In the case of aluminum cans, they arrive at the factory in bulk and are depalletized before being sent through an inverted high-pressure air rinsing system that removes any dust or debris. For PET and glass bottles, the process is more intensive. PET bottles are first blown into shape from preforms using heated molds, while glass bottles go through a multi-step washing process that includes detergent cleaning, high-temperature rinsing, and sterilization with ozone-treated water. Once the containers are sanitized and ready for filling, they move along conveyor belts to the high-speed filling machines. These machines operate with incredible efficiency, using precision nozzles to dispense the exact amount of cherry Coca-Cola into each container. One of the biggest challenges in this step is ensuring that carbonation is preserved during filling. To prevent excessive foaming and carbonation loss, the filling machines use counter-pressure technology. This involves pressurizing the container with CO2 before filling it with the beverage, ensuring that the carbonation remains intact and that there is minimal oxygen exposure. As the bottles and cans are filled, they are closely monitored by sensors and automated quality control systems to ensure that the correct fill levels are maintained. Any underfilled or overfilled containers are automatically rejected from the line. The next critical step is sealing, where each container is securely closed to lock in freshness. For aluminum cans, an automated seaming machine places a lid on top of the can and crimps it into place, creating an airtight seal. For plastic bottles, tamper-evident caps are applied using high-speed capping machines, while glass bottles are typically sealed with either twist-off metal caps or traditional crown caps. Immediately after sealing, the filled containers go through a pasteurization or cold sterilization process depending on the packaging type and regional regulations. In some cases, cherry Coca-Cola undergoes flash pasteurization, where the beverage is rapidly heated and cooled to kill any potential microorganisms without altering the taste. However, for many markets, Coca-Cola products are aseptically filled, meaning that the entire bottling process is conducted under sterile conditions, eliminating the need for heat treatment. Once the sealing and sterilization process is complete, the bottles and cans move to the labeling and packaging stage. This is where branding and product information are applied to each container, ensuring that the final product meets regulatory requirements and maintains Coca-Cola's iconic visual identity. Now that the cherry Coca-Cola has been bottled and sealed, the next phase of the manufacturing process focuses on quality control and inspection. Every single can and bottle must meet Coca-Cola's strict global quality standards before it can be shipped to retailers. This process involves multiple layers of testing, from automated inspections on the production line to detailed laboratory analysis conducted by food scientists. Even the smallest deviation in taste, carbonation level, or packaging integrity can result in a batch being rejected, ensuring that only the highest quality product reaches consumers. The first step in quality control takes place immediately after the filling and sealing process. High-speed vision inspection systems are installed along the conveyor belts, using advanced cameras and sensors to examine each bottle and can for defects. These systems check for issues such as underfilled or overfilled containers, misaligned caps, dents in cans, or improperly applied labels. If a container does not meet specifications, it is automatically removed from the line by a rejection mechanism. This automated inspection process allows for the real-time elimination of defective products, preventing inconsistencies from reaching the market. Another crucial quality control measure is the carbonation and pressure test. Since cherry Coca-Cola's signature fizz is one of its defining characteristics, it is essential to ensure that each bottle and can contains the correct amount of dissolved CO2. To verify this, a random selection of containers is taken off the production line and placed into a specialized testing chamber where their internal pressure is measured. If the pressure falls outside the acceptable range, this could indicate improper carbonation levels, a sealing defect, or temperature fluctuations during the filling process. If an issue is detected, adjustments are made to the carbonation equipment to maintain consistency across the batch. Next, samples from each production run are sent to the on-site laboratory for detailed chemical and sensory analysis. Here, trained food scientists perform a variety of tests to confirm that the cherry Coca-Cola meets Coca-Cola's strict formulation guidelines. One of the first tests conducted is the Brix test, which measures the concentration of dissolved sugars in the beverage. Since cherry Coca-Cola has a carefully calibrated sweetness level, any deviation in the Brix measurement could indicate an incorrect syrup-to-water ratio, requiring adjustments in the proportioner. Another key laboratory test is pH analysis. The acidity of cherry Coca-Cola is a crucial component of its taste, and this is largely controlled by the phosphoric acid content. A pH meter is used to measure the beverage's acidity, ensuring that it falls within the required range. Any variation in pH can significantly affect the drink's flavor balance, so this test is performed regularly to maintain consistency. Sensory evaluation is another critical aspect of quality control. A panel of trained taste testers, known as a sensory panel, is responsible for conducting blind taste tests to ensure that each batch of cherry Coca-Cola matches the expected flavor profile. These experts are highly trained to detect even the slightest differences in sweetness, acidity, carbonation, and cherry flavor intensity. They compare samples from the production line with reference samples from previous batches, ensuring that the taste remains uniform across all locations. If any inconsistencies are detected, adjustments are made to the formulation or processing parameters before the product is released for distribution. Packaging integrity is also a major focus of the quality control process. Even if the beverage itself meets all specifications, the packaging must be flawless to ensure product safety and shelf stability. To test this, random samples of filled bottles and cans undergo extreme stress testing. For plastic bottles, drop tests are conducted to simulate potential impacts during transportation. The bottles are dropped from various heights to ensure that they do not crack, leak, or experience cap failure. Cans are subjected to compression tests, where a machine applies controlled pressure to verify their structural integrity. If a can is too weak, it could deform or burst under normal handling conditions. If it is too rigid, it could indicate an issue with the aluminum thickness or the pressurization process. These tests help ensure that every container is durable enough to withstand shipping, storage, and handling by consumers. Another important quality control step is microbiological testing. Although cherry Coca-Cola's high acidity and carbonation naturally inhibit microbial growth, samples are still tested for the presence of bacteria, yeast, or mold. Microbiological testing is performed in a sterile laboratory environment where beverage samples are incubated under controlled conditions to detect any signs of microbial contamination. Even though Coca-Cola products are manufactured in sterile conditions, this extra layer of safety ensures that no contamination occurs at any stage of production. After all of these quality control tests have been completed, the final step before distribution is the batch coding and tracking process. Each bottle and can is printed with a unique production code that contains information about the manufacturing date, production line, and facility location. This allows Coca-Cola to track every product from the factory to store shelves. If an issue is ever discovered in a specific batch, this coding system enables rapid identification and recall of affected products. Once the cherry Coca-Cola has passed all quality control tests, the final phase of production involves packaging and distribution. This step ensures that the product is properly grouped, protected, and efficiently transported from the factory to retailers worldwide. The packaging process is highly automated and designed to handle the massive volume of cherry Coca-Cola produced daily while maintaining efficiency, accuracy, and product integrity. The first step in packaging is grouping the bottles and cans into multi-packs. Depending on the market and retail preferences, Cherry Coca-Cola is sold in a variety of formats, including single cans, 6-packs, 12-packs, and larger 24-pack cases. The process begins with an automated system that arranges the bottles or cans into the correct configuration for packaging. High-speed robotic arms carefully align the containers into precise rows, ensuring uniformity before wrapping or boxing. These systems are programmed to adjust the layout based on production requirements, allowing flexibility in the types of multi-packs produced. For aluminum cans, a shrink wrapping system is used to bundle them together into multi-packs. The cans pass through a conveyor where they are tightly wrapped in a thin but durable layer of plastic film. This film is then heated in a specialized tunnel, shrinking it around the cans to create a secure and tamper-proof bundle. This method provides stability during transportation while allowing consumers to easily separate individual cans when needed. In some cases, paperboard carriers are used instead of plastic shrink wrap, particularly in regions where sustainability initiatives encourage the reduction of plastic packaging. These carriers are die-cut to hold the cans securely while allowing easy removal. For plastic bottles, the process differs slightly. Many multi-packs of plastic bottles are held together using plastic rings or shrink-wrapped trays. Larger cases of Cherry Coca-Cola bottles are placed into corrugated cardboard boxes for additional protection. The use of recyclable materials is prioritized wherever possible to reduce environmental impact. Coca-Cola has implemented sustainable packaging solutions such as biodegradable plant-based plastics and recyclable wrapping materials to minimize waste. Some factories have also introduced lighter weight PET bottles that require less plastic while maintaining the same durability, further contributing to environmental goals. Once the Cherry Coca-Cola bottles and cans are securely packed, they move to the palletization stage. A palletizer is a large automated machine that carefully stacks the packaged products onto wooden or plastic pallets in an optimized arrangement for stability. This process ensures that products do not shift or fall during transport. Each pallet is carefully configured to maximize space while maintaining structural integrity. The palletizer is programmed to create stable layers of product, with each row strategically positioned to distribute weight evenly. After the pallets are loaded, they are wrapped with industrial-strength plastic film to keep them secure. This stretch wrapping process ensures that the products remain stable during transport. In some cases, pallets are reinforced with corner protectors for additional stability, particularly when shipping long distances. Some facilities also use robotic pallet wrappers, which automatically detect the height and dimensions of each pallet to apply the precise amount of stretch film required for stability without excessive material use. Once wrapped, the pallets are labeled with tracking codes and barcodes that contain critical shipment information, including the product type, batch number, expiration date, and destination details. These labels ensure that the inventory can be accurately tracked throughout the supply chain, reducing the risk of misdelivery or loss. The tracking system also allows retailers to quickly verify shipments upon arrival and enables Coca-Cola to monitor stock movement and demand trends. The next step is warehouse storage and inventory management. Once the Cherry Coca-Cola pallets are prepared, they are transported via forklifts to massive storage warehouses. These warehouses are temperature controlled to protect the beverage from excessive heat or humidity, which could affect carbonation levels or packaging integrity. Temperature regulation is especially important in regions with extreme climates, as fluctuations in temperature could cause the CO2 in the beverage to expand or contract, potentially leading to leaks or compromised carbonation. Advanced inventory management systems track every pallet, using barcodes and RFID technology to ensure efficient organization and retrieval. These systems automatically log incoming and outgoing shipments, allowing real-time monitoring of stock levels. Warehouses are organized using automated retrieval systems that move pallets using robotic arms and conveyor systems, further increasing efficiency in high-volume distribution centers. Once the products are stored, the logistics and distribution phase ensures that Cherry Coca-Cola reaches retailers and consumers as quickly as possible. The logistics team carefully plans delivery routes based on demand, ensuring that distribution centers and retail locations receive fresh stock on schedule. The distribution model varies depending on the region, with some locations utilizing central distribution hubs that serve multiple retailers, while others ship directly from production facilities to large supermarket chains and wholesalers. Trucks are loaded with pallets of Cherry Coca-Cola according to a strict loading schedule, ensuring that the oldest inventory is shipped first to maintain freshness. The loading process is carefully coordinated to optimize space while keeping products stable during transit. Many of these trucks are refrigerated or climate controlled, particularly in warmer regions, to prevent heat exposure that could compromise product quality. In some cases, insulated truck liners are used instead of full refrigeration, allowing for temperature control without the added energy cost of refrigerated transport. The process of making Pepsi begins with one of its most essential components, water. Water forms the majority of the final beverage, making its purification and preparation one of the most critical steps in the manufacturing process. PepsiCo takes extreme care in sourcing and treating water to ensure the final product is free from impurities, contaminants, and off flavors. Without this careful preparation, the beverage could have inconsistencies in taste, appearance, and carbonation retention. The journey starts with sourcing water from natural springs, municipal supplies, or underground wells, depending on the bottling plant's location. However, regardless of its origin, this water must go through extensive treatment to meet PepsiCo's strict quality standards. The process begins with initial screening, where water passes through coarse filters that remove large particles such as dirt, sand, and debris. This is followed by sedimentation, a method that allows heavier impurities to settle at the bottom while the cleaner water moves forward in the process. Once the larger impurities are removed, the next step is carbon filtration. This step is crucial for removing chlorine, organic compounds, and any unwanted odors or tastes that could interfere with the Pepsi formula. Activated carbon filters contain a highly porous material that traps chemical impurities while allowing pure water to flow through. This process not only improves the taste of the water, but also enhances its ability to mix well with the other ingredients later in production. But up next is the reverse osmosis process, one of the most advanced purification techniques used in beverage manufacturing. Reverse osmosis involves forcing water through an ultra-fine membrane under high pressure, effectively removing even the tiniest dissolved particles, including salts, minerals, and microscopic contaminants. This ensures that the water is as pure as possible before it becomes part of the Pepsi formula. To further refine the water, it undergoes ultraviolet sterilization. This step is essential for eliminating any remaining bacteria, viruses, or other microorganisms that could compromise the safety and shelf life of the beverage. High-intensity UV light disrupts the DNA of these microorganisms, rendering them inactive without the use of chemical disinfectants. Finally, before the purified water is stored, it goes through an ozonation process. Ozone, a highly reactive form of oxygen, is injected into the water to act as a natural sanitizer. This step ensures that the water remains free from microbial contamination while it is held in large stainless steel storage tanks, awaiting the next phase of production. Now that the water has been meticulously purified, it must be precisely balanced to create the ideal base for Pepsi. Even though reverse osmosis removes most dissolved solids, a controlled amount of specific minerals is added back into the water to optimize taste and improve its ability to retain carbonation. This step is carefully monitored as the mineral composition of the water can impact the final mouthfeel and texture of the beverage. With the water fully prepared and stored in sanitary tanks, it is now ready to be mixed with the other key ingredients that will give Pepsi its distinctive flavor. But before moving on to mixing, each batch of purified water is rigorously tested for quality. Samples are taken from the storage tanks and analyzed in PepsiCo's in-house laboratories. Scientists and quality control experts measure pH levels, mineral content, and overall purity, ensuring that each batch meets the company's global standards. If any irregularities are detected, the water is either reprocessed or discarded, preventing any inconsistencies from affecting the final product. Now that the water has been meticulously purified and stored in sanitized tanks, the next crucial step in the Pepsi manufacturing process is the preparation and addition of sweeteners. Sweeteners play a fundamental role in defining the flavor profile of Pepsi, contributing to its signature taste while also affecting mouthfeel, viscosity, and overall balance. The selection, processing, and precise blending of these sweeteners are critical to ensuring that every bottle and can of Pepsi maintains consistency across different production facilities worldwide. In most regions, Pepsi is sweetened with high fructose corn syrup, a liquid sweetener derived from cornstarch. However, in some markets, particularly in countries where cane sugar is more widely available or preferred, sucrose from sugarcane or sugar beets is used instead. Regardless of the source, the sweetener must be carefully refined and processed before being added to the beverage. The journey of high fructose corn syrup begins with corn milling, where harvested corn is cleaned, steeped, and ground into a slurry to separate the starch from the fiber, protein, and germ. The extracted starch is then subjected to enzymatic processing, where it is converted into glucose. A second enzyme is introduced to transform a portion of the glucose into fructose, increasing its sweetness. The result is a thick, viscous syrup that is then further refined, filtered, and tested to ensure the correct balance of glucose and fructose. The most commonly used variety in soft drinks is HFCS 55, which contains approximately 55% fructose and 45% glucose, closely mimicking the sweetness profile of cane sugar. For regions that use sucrose instead of HFCS, the sugar is derived from either sugarcane or sugar beets. Sugarcane is harvested, crushed to extract juice, and then boiled to concentrate the sugar, forming crystallized sucrose. Sugar beets, on the other hand, are sliced and soaked in hot water to extract sugar, which is then purified and crystallized. In both cases, the raw sugar undergoes extensive refining to remove impurities and ensure a uniform, pure sweetener. Once the sweetener is ready, it must be dissolved into a concentrated syrup before being mixed with other ingredients. In a dedicated mixing tank, the high fructose corn syrup, or dissolved sucrose, is blended with purified water in precise proportions to create a uniform, sweetening solution. This syrup is continuously agitated to prevent crystallization and ensure a consistent texture. To maintain Pepsi's exact sweetness level, refractometers are used to measure the syrup's sugar concentration, ensuring it falls within the specified range. At this stage, the syrup is also subjected to rigorous quality control testing. Laboratory technicians take samples from each batch and analyze them for purity, consistency, and microbial safety. Any inconsistencies in sweetness or viscosity could alter the taste of the final product, so adjustments are made, if necessary, before moving on to the next step. Now that the sweetener has been perfectly prepared, it is time to introduce the key flavoring components that define Pepsi's distinctive taste. Pepsi's flavor is the result of a complex blend of natural and artificial flavorings, including citrus oils, spice extracts, and caramel notes. The exact recipe remains a closely guarded secret, known only to a select few within the company, but it is widely understood that ingredients like orange oil, lemon oil, vanilla, cinnamon, nutmeg, and cola nut extract contribute to the drink's signature profile. The flavoring components are carefully blended into a concentrated mixture known as the flavor base. This highly concentrated liquid is prepared in a separate, sterile mixing tank, where precise measurements of each ingredient are combined under controlled conditions. Some of these ingredients, particularly the essential oils, must be emulsified using stabilizers to ensure they mix properly with the water-based formula of Pepsi. Without proper emulsification, the oils could separate from the rest of the beverage, leading to inconsistent flavor distribution. Phosphoric acid is then added to the flavor base, providing Pepsi with its signature sharpness and tangy aftertaste. This acid also plays a crucial role in preserving the beverage by inhibiting microbial growth. The level of acidity is carefully controlled to balance the sweetness of the drink and enhance its overall flavor. Caramel color, which gives Pepsi its deep brown hue, is another essential ingredient added at this stage. This colorant is created by heating sugar compounds under controlled conditions, resulting in a stable and safe coloring agent. The intensity of the caramel color is strictly regulated to ensure that every bottle of Pepsi has the same visual appeal. Once the flavor base is complete, it must be thoroughly mixed with the sweetener solution to create the final syrup that will be used in the soft drink. This blending process takes place in large stainless steel tanks, where high-powered mixers ensure even distribution of all ingredients. The proportion of sweetener to flavor base is precisely measured, as even a slight deviation could alter the taste of the final product. Before the syrup is approved for use, samples are taken and analyzed in a quality control lab. Tests include pH measurement, viscosity checks, and sensory evaluations, where trained tasters confirm that the syrup matches Pepsi's standard flavor profile. These rigorous quality checks ensure that every batch of syrup is identical, maintaining Pepsi's global consistency. Once the syrup has passed all quality control tests, it is stored in temperature-controlled holding tanks, ready to be mixed with carbonated water. These tanks are kept under strict sanitary conditions to prevent contamination and preserve the integrity of the syrup. But up next is one of the most critical aspects of the Pepsi production process: carbonation. This step is responsible for the effervescence and refreshing sensation that consumers associate with soft drinks. Without proper carbonation, Pepsi would lose its signature fizz, altering the drinking experience. The process of infusing the beverage with carbon dioxide is both a science and an art, requiring precise control over temperature, pressure, and gas concentration. To begin the carbonation process, purified water is first chilled to near freezing temperatures. The reason for this is that carbon dioxide dissolves more efficiently in cold water than in warm water, ensuring maximum carbonation retention. The chilled water is then injected with high purity CO2 gas under controlled pressure, creating carbonated water. This water is then carefully blended with the pre-mixed syrup in an exact ratio, typically around 5 parts carbonated water to 1 part syrup. The precise proportion ensures the correct balance of flavor, sweetness, and fizziness in the final beverage. Maintaining the right level of carbonation is crucial, as it directly affects the mouthfeel and shelf life of the product. If the carbonation is too low, the drink will taste flat and less refreshing. If it is too high, the beverage may be overly acidic or cause excessive foaming during packaging. To ensure consistency, carbonation levels are continuously monitored using pressure sensors and dissolved CO2 analyzers. The newly carbonated Pepsi must now be handled carefully to prevent the loss of carbonation before packaging. At this stage, the beverage is kept under constant pressure in specialized holding tanks to maintain CO2 solubility. Any sudden release of pressure could cause the carbon dioxide to escape, resulting in a less fizzy drink. With the Pepsi now fully mixed, carbonated, and held under precise pressure conditions, The next step is bottling and packaging. This is one of the most intricate parts of the manufacturing process, requiring extreme precision, speed, and cleanliness to ensure that every bottle and can of Pepsi is filled, sealed, and prepared for distribution without losing carbonation or quality. The bottling process must take place in a sterile environment to prevent contamination, and the machinery involved operates at incredibly high speeds to keep up with global demand. The first part of this process involves the preparation of bottles and cans. Pepsi is available in a wide range of packaging formats, including glass bottles, aluminum cans, and plastic bottles made from polyethylene terephthalate. Each type of container has its own preparation requirements, but all must be thoroughly cleaned and sterilized before being filled. For plastic bottles, the process begins with small, preformed PET molds called preforms. These preforms are heated to a specific temperature and then rapidly inflated using high-pressure air inside a blow molding machine. This machine expands the preforms into their final bottle shape, ensuring uniform thickness and durability. The freshly molded bottles are then conveyed into a high-speed rinsing station, where they are thoroughly washed with filtered water and food-safe sanitizing agents to remove any potential contaminants. Glass bottles undergo a more rigorous cleaning process since they are often reused. They are first soaked in a high-temperature caustic solution to break down any residue from previous use, followed by multiple rinses with clean, filtered water. Finally, they pass through a steam sterilization chamber to ensure that no microorganisms remain. Aluminum cans, on the other hand, arrive at the bottling plant pre-formed and ready to be filled. However, before filling, they are sent through a high-pressure air jet cleaning system that blasts away dust and debris. Since aluminum cans are highly sensitive to corrosion, a thin food-safe lining is applied inside each can to prevent any reaction between the beverage and the metal. Now that the bottles and cans are fully prepared, the filling process can begin. The carbonated Pepsi is transported through a network of pressurized stainless steel pipes that maintain the beverage's optimal CO2 concentration and temperature. The filling machines operate at high speeds, capable of processing thousands of containers per minute. For PET and glass bottles, filling is done using gravity-based or counter-pressure filling systems. In a counter-pressure system, the bottle is first pressurized with CO2 before the Pepsi is introduced. This prevents foaming and excessive carbonation loss during filling. The precise amount of liquid is dispensed into each bottle, with sensors ensuring that no underfilled or overfilled bottles proceed down the production line. Aluminum cans require a slightly different approach. Since they are more prone to CO2 loss due to their wide openings, the filling nozzles are designed to minimize turbulence as the liquid enters. The cans are quickly filled and then topped with a small injection of nitrogen gas to prevent oxidation before being sealed. Now that the containers are filled with carbonated Pepsi, the next critical step is sealing. This process must be done immediately after filling to prevent carbonation loss and contamination. For plastic and glass bottles, this involves capping. Screw-on plastic caps are applied to PET bottles using high-speed rotary capping machines, which tighten each cap with precise torque to ensure a secure seal. Glass bottles, often used for premium or international markets, are sealed with either metal crown caps or twist-off caps, depending on the region. Aluminum cans are sealed using a double seaming process. A lid, which contains an integrated pull tab, is placed on top of the can and then mechanically crimped around the rim. This creates an airtight seal that locks in carbonation and prevents leakage. With all the containers now sealed, they move on to the quality control phase. At this stage, random samples are pulled from the production line and tested for multiple factors, including fill level, carbonation retention, pressure stability, and contamination. Advanced X-ray and laser scanning systems inspect each bottle and can to ensure that there are no foreign particles, dents, or defects in the packaging. Any defective units are immediately rejected and removed from the batch. Once the beverages pass quality control, the containers proceed to labeling. Each bottle and can receives a label that includes branding, nutritional information, ingredient lists, and regulatory compliance markings. PET bottles have labels applied using heat shrink or pressure-sensitive label machines, while aluminum cans typically have their designs pre-printed onto the metal surface. After labeling, the bottles and cans are grouped into multi-packs for retail distribution. This process involves bundling them into various configurations, such as 6-packs, 12-packs, or full cases. Plastic shrink wrap, cardboard trays, or molded carrying handles are used to secure the multi-packs for easy transportation. The completed packs are then stacked onto pallets in an organized manner and wrapped in stretch film to stabilize them for shipping. Now it's time for one of the most logistically challenging aspects of Pepsi production: distribution. The pallets of finished Pepsi products are moved to temperature-controlled warehouses where they are stored before being shipped to retailers, grocery stores, vending machines, and restaurants. Since Pepsi is produced in enormous quantities to meet global demand, distribution logistics must be precisely managed to ensure that every store and vendor receives fresh products. Pepsi's supply chain is a highly coordinated operation involving fleet management, refrigerated storage, and just-in-time delivery systems. Large distribution centers act as hubs where shipments are sorted based on region and customer demand. Trucks, rail transport, and even cargo ships are used to move massive volumes of Pepsi across countries and continents. Once the products arrive at their final destinations, they are placed in cold storage or directly onto store shelves. In grocery stores and supermarkets, Pepsi is often stored in temperature-controlled sections to maintain freshness. Restaurants and fast food chains receive large volumes of Pepsi in bulk containers, which are connected to soda fountains for on-demand dispensing. Throughout this entire process, PepsiCo maintains strict inventory tracking and quality assurance programs. Each batch of Pepsi is assigned a unique tracking code, allowing the company to trace products back to their production date, location, and ingredient sources. This ensures that in the event of a recall or quality issue, affected products can be quickly identified and removed from circulation. With the Pepsi bottles and cans now filled, sealed, labeled, and packed for distribution, one of the final but most crucial aspects of the manufacturing process is ensuring product consistency, longevity, and consumer satisfaction. Maintaining Pepsi's signature taste and quality across millions of bottles and cans requires an advanced system of quality control, storage optimization, and packaging innovation. Every aspect, from the shelf life of the product to the materials used in packaging, plays a role in ensuring that each Pepsi delivered to a consumer is as fresh and enjoyable as the last. The first key factor in Pepsi's shelf life and consistency is its ability to retain carbonation over time. Carbonation, which gives Pepsi its signature fizziness, is created by dissolving carbon dioxide into the liquid under high pressure. The challenge is ensuring that this CO2 remains trapped within the beverage from the moment it is bottled until it is opened by the consumer. To maintain carbonation, Pepsi uses specially designed bottles and cans that act as airtight barriers, preventing CO2 from escaping. Plastic bottles made from polyethylene terephthalate are engineered with multiple layers that slow down gas diffusion, preventing CO2 from seeping out over time. The thickness and structure of PET bottles are carefully optimized to balance durability with weight, ensuring that the bottles are strong enough to retain carbonation while remaining lightweight for transportation. Aluminum cans provide an even better barrier against gas loss. Their completely sealed structure ensures that no CO2 escapes, preserving the drink's fizziness for extended periods. Additionally, A protective food-grade lining inside each can prevent any reaction between the metal and the beverage, which could otherwise affect flavor. Glass bottles, often used for premium markets or limited edition versions of Pepsi, offer the best gas retention of all packaging types. Glass is completely impermeable, meaning that Pepsi stored in glass bottles maintains its carbonation for the longest period. However, glass is heavier and more fragile than plastic or aluminum, making it less practical for mass production and distribution. Another critical factor in product longevity is preventing oxidation. Exposure to oxygen can alter the taste of Pepsi, causing it to become flat and develop off flavors over time. To counter this, PepsiCo employs nitrogen dosing in certain packaging lines. This process involves injecting a small amount of nitrogen gas into PET bottles just before sealing. The nitrogen displaces any residual oxygen inside the bottle, reducing the risk of oxidation while also adding structural rigidity to the bottle, preventing it from collapsing under vacuum pressure. Beyond carbonation and oxidation control, preservatives also play a role in maintaining Pepsi's freshness. While the beverage's acidity and carbonation naturally inhibit microbial growth, additional preservatives such as sodium benzoate are included to extend shelf life further. These preservatives prevent mold, yeast, and bacterial growth, ensuring that Pepsi remains safe for consumption for months or even years after production. Now that the beverage's stability is secured, it must be stored and transported under optimal conditions. Pepsi is highly sensitive to temperature fluctuations, which can affect carbonation retention and overall flavor. As a result, warehouses, distribution centers, and retail storage areas are kept within a controlled temperature range to prevent heat exposure. Excessive heat can accelerate CO2 loss in plastic bottles and increase oxidation reactions, leading to a flatter, less refreshing drink. To counteract this, refrigerated warehouses are used in regions where high temperatures could compromise product quality. During transportation, trucks equipped with climate control ensure that Pepsi is not exposed to extreme heat or direct sunlight, both of which could degrade the beverage. Another major factor that affects Pepsi's taste consistency is the impact of light exposure. Ultraviolet light can break down some of the organic compounds in Pepsi's flavoring, leading to unwanted taste changes. This is why Pepsi bottles, particularly those made from PET, are designed with tinted or opaque plastic to reduce UV penetration. Aluminum cans and glass bottles naturally provide complete light protection, further ensuring product stability. Once Pepsi reaches its final retail destinations, whether in grocery stores, vending machines, or fast food chains, it is crucial that storage guidelines continue to be followed. Retailers are instructed to keep Pepsi stock rotated, ensuring that older products are sold first and newer shipments are stored properly. This helps maintain product freshness for consumers while preventing expired stock from sitting on shelves. Fast food chains and restaurants that serve Pepsi from soda fountains have additional steps to ensure taste consistency. Instead of pre-packaged bottles and cans, Pepsi is delivered to these locations in large pressurized syrup containers known as bag-in-box systems. These containers hold concentrated Pepsi syrup, which is mixed with carbonated water on demand through specialized dispensing machines. The bag-in-box system allows for efficient storage and prevents waste, as restaurants can control the syrup-to-water ratio for optimal taste. These systems are regularly maintained, with filters and carbonation settings adjusted to match the ideal flavor profile. Additionally, PepsiCo provides restaurants with quality control tools to measure CO2 levels and syrup concentration, ensuring that every poured glass tastes as good as a bottled Pepsi. With all these measures in place, Pepsi is now fully ready for consumers to enjoy. But beyond the immediate production and distribution, PepsiCo continually invests in research and development to improve manufacturing efficiency, sustainability, and packaging innovations. One of the company's most significant focuses in recent years has been reducing the environmental impact of its packaging. PepsiCo has made major advancements in recyclable PET bottle technology, developing bottles that contain post-consumer recycled plastic to cut down on waste. Additionally, the company has experimented with plant-based PET alternatives that reduce reliance on petroleum-based plastics. Aluminum cans have also been a major target for sustainability improvements. Since aluminum is highly recyclable, PepsiCo has worked to increase the amount of recycled aluminum used in can production. The company encourages consumers to participate in recycling programs, ensuring that cans are properly collected and reused. In some markets, PepsiCo has even introduced refillable glass bottle programs, allowing consumers to return used bottles for sanitation and reuse, significantly cutting down on single-use waste. Further technological advancements in bottling machinery have also improved efficiency in the production process. The industrial processing of honey begins not within the walls of the factory, but at the apiaries, where honeybees forage, collect nectar, and begin the complex enzymatic process of transforming floral sugars into the thick, golden liquid we know as honey. Factory-scale honey production starts with the careful coordination between contracted beekeepers and processing plants, which work together to supply bulk honey at a scale large enough to support mass distribution. The first step in the factory process involves the reception and inspection of raw honey as it arrives from the beekeepers' extraction sites. Raw honey is typically delivered in large food-grade steel drums or plastic totes, each capable of holding hundreds of pounds of honey. These containers arrive sealed, labeled with origin data, floral source if known, and batch tracking codes. Upon arrival at the honey processing facility, each container is unloaded onto the receiving dock, where a team of technicians begins the initial quality assurance process. This is far more than a visual check. Industrial honey processors must guarantee that the incoming product is pure, unadulterated, and meets strict legal and food safety standards. The drums are first sampled using a specialized honey sampling spear, a long stainless steel tube designed to pierce through the viscous mass and extract a vertical core from top to bottom. This is essential because honey can stratify with moisture content, color, and crystallization levels varying from top to bottom. The extracted sample is then homogenized and sent to the quality control laboratory. Here, a battery of tests is performed. Moisture content is measured using refractometers, which determine how much water is present in the honey. Legal standards require honey to contain no more than 20% moisture to prevent fermentation. Beyond moisture testing, analysts perform pollen analysis to verify floral sources and geographic origin, which is important for regulatory labeling and for upholding claims like clover honey or orange blossom honey. Additional tests, such as electrical conductivity, help differentiate between nectar and honeydew honeys, while HMF levels, or hydroxymethylfurfural, are checked to ensure the honey hasn't been exposed to excessive heat during prior storage or transit. High-performance liquid chromatography may also be used to detect the presence of added sugars, which would indicate adulteration and result in immediate rejection of the batch. Once a drum passes inspection and is approved for processing, it is moved to the uncrystallization station. Raw honey can crystallize over time, particularly when stored in cooler environments or when the floral source is rich in glucose. Crystallized or partially crystallized honey must be re-liquefied before it can be filtered or blended. This is achieved by placing the drums in heated chambers or warm water baths, known as hot rooms, where they are gently warmed to temperatures around 95 to 110 degrees Fahrenheit. This temperature range is sufficient to melt crystals without degrading the honey's delicate aromatic and enzymatic properties. Large facilities often use drum heating tunnels that can accommodate dozens of drums at a time. These tunnels employ radiant heat panels and convection fans that maintain a steady, uniform temperature throughout the enclosure. Temperature probes are inserted into each drum to ensure that internal temperatures rise slowly and evenly, preventing localized overheating which could darken the honey or degrade its quality. This gentle warming process can take anywhere from 24 to 72 hours, depending on the degree of crystallization and the initial temperature of the honey when it arrived. Now it's time to go into the liquefaction and transfer stage, where the now softened honey is pumped out of the drums and into the factory's primary processing line. This step requires specialized food-grade pumps capable of handling thick, sticky materials without introducing air bubbles or damaging the honey's texture. Positive displacement pumps, such as rotary lobe or progressive cavity pumps, are commonly used for this purpose. These pumps are designed to move viscous fluids at a steady rate without causing foaming or aeration, which can negatively impact downstream processing. As the honey is pumped from each drum, it passes through heated stainless steel pipelines that maintain a consistent temperature, usually around 110 to 120 degrees Fahrenheit, to keep the honey fluid during transit. The pipelines are insulated to minimize heat loss, and the entire system is cleaned between batches using CIP or clean-in-place systems, which circulate hot water and food-safe cleaning agents to maintain sanitary conditions. Valves and flow meters are used to control how much honey enters the next phase, which is usually a settling or holding tank. These tanks are large vertical silos equipped with gentle agitation paddles to keep the honey uniform without whipping air into it. At this stage, the honey is allowed to rest briefly, giving suspended particles like wax fragments, bee parts, or pollen clumps time to rise or settle. Some facilities incorporate slow-flow decanting chambers or skimming belts that remove surface foam and floating debris. The goal here is to prepare the honey for the critical filtration stage without exposing it to excessive agitation or temperature shifts, which could compromise quality. But up next is the filtration stage, one of the most technically controlled steps in factory honey processing. The challenge with filtering honey lies in removing impurities while preserving beneficial properties such as flavor, aroma, and trace pollen content. To accomplish this, processors use a series of progressively finer filters, starting with coarse metal mesh screens and moving to finer, micron-level filtration pads or cartridges. Initially, the honey flows through vibratory sieve filters or centrifugal strainers that remove large debris, including chunks of wax or bee remnants. These are often equipped with auto-cleaning screens that rotate or vibrate to prevent clogging. After coarse filtering, the honey enters a fine filtration system. Depth filters composed of cellulose or food-grade polypropylene are commonly used. These filters remove particles as small as 5 to 10 microns, including residual wax, dust, and crystallized sugar particles that could initiate recrystallization in the final product. To aid this process, the honey is maintained at a precise temperature of about 120 to 130 degrees Fahrenheit, warm enough to reduce viscosity and improve flow through filters, but not so hot as to destroy heat-sensitive enzymes or antioxidants. Inline temperature sensors and automated control panels ensure that every gallon of honey is processed under identical thermal conditions. Some advanced facilities even use vacuum-assisted filtration to further reduce the need for high temperatures, thereby preserving more of the honey's raw characteristics. Once filtration is complete, the honey is collected in large stainless steel blending tanks. These tanks are used to homogenize different batches of honey, standardize flavor profiles, and adjust final parameters such as color and clarity. Mixing paddles rotate at slow, controlled speeds to avoid aeration while ensuring a uniform blend. It's at this stage that some producers may add trace amounts of previously tested and approved batches to maintain flavor consistency across large volumes, especially if multiple floral sources are involved. Now it's time to explore the homogenization process in more detail, as this step plays a pivotal role in ensuring that every bottle or jar of honey pulled from the line is virtually identical in texture, color, and taste. Honey, being a natural product, can vary widely between batches due to differences in nectar sources, collection times, and even seasonal variations. To manage these inconsistencies, processors rely on computer-controlled blending protocols that match incoming honey against established reference standards. Before blending begins, technicians perform sensory and analytical testing on the batch, including color measurement using the Fund scale, which classifies honey from water white to dark amber. Flavor notes are assessed by trained sensory panels or electronic nose devices, while moisture and acidity levels are verified to determine blending ratios. If a batch is slightly darker than the standard product line, a portion of lighter honey is added to balance the color. If a batch is too viscous, a blend with a slightly higher moisture content is introduced to bring the final viscosity within specification. Mixing tanks used in this process are often jacketed with warm water or glycol to maintain the blending temperature at a steady 110 to 120 degrees Fahrenheit. Internal baffles guide the flow of honey, ensuring thorough integration without the formation of dead zones or stratification. The tanks are usually equipped with inline sensors that continuously monitor parameters like Brix, viscosity, and turbidity. The blending cycle may take several hours for large volumes, and throughout the process, automated samplers pull small amounts at regular intervals to verify that the blend remains within quality parameters. Once homogenization is complete, the honey is transferred to the final holding tanks that feed directly into the packaging lines. These tanks are placed on load cells that precisely measure the volume of honey dispensed into each container. From this point forward, the product must move through sealed, temperature-controlled systems to ensure no contamination occurs before bottling. And that leads directly into the highly synchronized packaging phase. As the homogenized honey flows from the final holding tanks into the packaging system, the entire process becomes a high-speed, tightly orchestrated sequence of mechanical precision and hygiene control. This stage is where the product begins to take on its final consumer-facing form, whether it's packaged in squeeze bottles, glass jars, tubs, or bulk containers. The packaging line starts with the selection and preparation of containers, which are fed into the system from large hopper units or depalletizers, depending on the container type. Plastic bottles often arrive pre-formed and stacked in bulk, while glass jars may come in pallets wrapped in protective plastic film. Regardless of material, every container goes through a rigorous cleaning phase before it is allowed anywhere near the honey. The first step in container preparation is an air rinse or ionized air cleaning process. Each container is inverted and passed through a chamber where blasts of filtered, pressurized air are directed inside. Ionized air is used specifically to neutralize any static charges that might cause dust or particles to cling to the sides of the container. In glass packaging lines, this process may be supplemented with a vacuum extractor that removes dislodged particles immediately after the air rinse. Some facilities also opt for a UV light exposure chamber that the containers pass through as an added antimicrobial safeguard. All of these steps are executed on automated conveyor systems, synchronized to keep pace with the fill line. Now it's time to go into the filling stage, which must be executed with extreme accuracy to ensure every package contains the correct weight or volume of honey. Honey's thick, slow-moving consistency makes it a challenging product to fill efficiently at scale. To meet this challenge, factories use volumetric piston fillers or gear pump filling machines, both of which are well suited for handling viscous, sticky products. These machines are equipped with heated nozzles and jacketed tubing to maintain the honey at an optimal temperature, typically around 110 degrees Fahrenheit, so it flows smoothly without foaming or dribbling. Each filling station is designed with multiple nozzles, often ranging from 4 to 16, depending on the line's speed and scale. The nozzles are programmed to descend into the containers during filling and retract as the level rises, a method known as bottom-up filling. This minimizes splashing and helps prevent the introduction of air bubbles, which can interfere with the product's shelf stability and aesthetic appearance. Inline check weighers are stationed just downstream of the filling heads, automatically rejecting any underfilled or overfilled containers from the line. Any deviation outside a narrow tolerance window triggers an immediate alert and mechanical removal. Immediately after filling, the containers are transferred to the capping and sealing station. For plastic bottles, this often involves a torque-controlled capper that applies precise rotational force to ensure a tight but not damaging seal. Flip-top caps, disc-top caps, or screw caps are automatically sorted and fed into place using vibratory feeders and cap chutes. In the case of glass jars, the capping process may involve steam vacuum sealing with metal lids, creating a hermetic seal that ensures freshness and shelf stability. As the lid is applied, a puff of steam is injected into the headspace, which condenses and creates a partial vacuum as the jar cools. Some packaging lines also include an induction sealing station. This involves placing a foil liner inside the cap, which is then sealed to the lip of the container using electromagnetic induction to heat and bond the foil to the rim. This creates a tamper-evident barrier that reassures consumers while also acting as an additional contamination safeguard. Once sealed, the containers pass through a water or air rinse to remove any stray honey drips from the filling station, followed by a drying tunnel that uses forced warm air to eliminate surface moisture before labeling. But up next is the labeling and coding process, where the honey finally begins to take on its retail-ready appearance. Labeling machines apply product labels at high speed using pressure-sensitive or shrink-sleeve labels, depending on the packaging format. Pressure-sensitive labels are peeled from a backing roll and applied to the container with rollers, while shrink-sleeve labels are wrapped around the container and heat-shrunk into place using a steam tunnel. Each label is applied with extreme precision using optical sensors that detect the exact placement zone, ensuring uniformity across all units. At this point, the line integrates the critical traceability step, date coding, and batch identification. Inkjet or laser coders are installed directly after the labeling station and are configured to print the production date, batch number, and expiration date onto the label, cap, or bottleneck. These codes are essential for tracking product back to its source in the event of a recall or quality issue, and they also help with inventory rotation throughout the supply chain. Vision systems verify the presence and legibility of these codes, and any container missing its code is automatically rejected from the line. Once labeled and coded, the honey containers move toward the secondary packaging phase. Here, they are grouped based on retail configuration, single bottles, multi-packs, or cartons, and loaded into larger corrugated cardboard cases. Robotic case packers or drop pack mechanisms handle this process with extreme care, particularly with glass containers, which require dividers and cushioning. Once the cases are assembled and filled, they're sealed using hot melt glue or tape and then passed through a check weigher to verify package weight consistency. The final stage in the packaging process is palletization, where filled cases are stacked in precise formations onto wooden or plastic pallets. Robotic palletizers equipped with vacuum grippers or mechanical arms lift and arrange the cases row by row, ensuring that weight is evenly distributed to prevent collapse during transport. Once the pallet is complete, it is wrapped with industrial stretch film to stabilize the load and protect it from moisture and dust. Each pallet receives a barcode label containing all relevant shipping and traceability data. including product type, quantity, destination, and handling instructions. Now it's time to go into the warehousing and distribution stage, which is vital to maintaining honey's shelf life and ensuring that product quality is preserved from the factory to the consumer. Honey is hygroscopic, meaning it absorbs moisture from the air, so warehousing conditions must be carefully controlled. Finished pallets are moved to temperature and humidity-controlled warehouse zones where the ambient environment is kept between 60 and 75 degrees Fahrenheit, with relative humidity below 60% to prevent moisture ingress that could lead to fermentation or spoilage. Inventory is managed using a warehouse management system that assigns each pallet a digital location code, tracks product age, and ensures first in, first out rotation. Automated guided vehicles or forklifts retrieve pallets based on shipping schedules, and every movement is recorded in a centralized database. This allows full traceability not just back to the packaging date, but all the way through blending batches and raw honey origins. If a quality issue were ever discovered post-shipment, the manufacturer could instantly identify and recall only the affected lot numbers. Before pallets leave the facility, they may undergo one final inspection. Logistics personnel verify that labels match the shipping documentation, confirm temperature logs for any time-sensitive products, and ensure that stretch wrapping and labeling meet the receiving distributor's requirements. Some retailers have specific palletization rules, like maximum stack height or barcode placement, that must be followed exactly to avoid supply chain disruptions. Once cleared, pallets are loaded into temperature-controlled trucks using dock levelers that ensure a smooth transition from warehouse to vehicle. These trucks are often equipped with sensors that track internal temperature and humidity levels during transit. If any threshold is breached during transportation, alerts are sent to the distribution center to allow preventive action. This step is critical because improper handling during shipping can undo months of careful processing. For instance, exposure to excessive heat can darken the honey, degrade its enzymes, and even trigger fermentation if the moisture content is borderline. As the honey moves through regional distribution centers and into retail outlets, it remains in sealed containers that shield it from light and air. Most honey has a shelf life of 2 years or more if stored properly, thanks to its low water activity and high sugar concentration, which naturally inhibit microbial growth. However, the quality and freshness perceived by the consumer are still closely tied to how well every part of the manufacturing and distribution process has been executed, from the bee to the bottle to the shelf. Every detail, every degree of heat, every micron of filtration, and every second of line timing plays a role in preserving the integrity of the final product. And even after it reaches store shelves, the story of how honey is made in a factory continues to resonate with precision, craftsmanship, and scientific control. To fully understand the industrial production of honey, it's important to go beyond the mechanics and explore the subtleties of product customization, regulatory compliance, and the final quality control processes that make factory-scale honey not just uniform, but legally marketable and consumer safe. After the honey has been packaged, palletized, and staged for distribution, another dimension of the process becomes active: the post-packaging quality assurance system. This system acts as a final safeguard to confirm that the product leaving the facility not only meets internal quality standards, but also complies with local, national, and international food safety laws. One of the most essential tasks during this final phase is the detailed sampling and archiving of batch samples. From each production lot, designated containers are pulled from the finished goods and sent to the factory's on-site analytical laboratory. These samples are catalogued, sealed, and retained in climate-controlled archives for up to several years, depending on regulatory requirements. This ensures that if a complaint, audit, or issue ever arises, the facility can test the retained sample and compare it to the current product in question. The archive system is tied directly into the facility's digital traceability records, allowing a sample to be matched instantly to the exact floral source. Filtration parameters, blend ratios, packaging date, and even which employee signed off on the batch. Parallel to this, comprehensive chemical and microbiological testing is performed on the pooled samples. Even though honey is naturally resistant to microbial growth due to its low water activity and high sugar content, every lot is still tested for yeast, mold, and spore-forming bacteria, such as Clostridium botulinum. The latter is especially critical for honey intended for infant consumption. Though honey is generally not recommended for children under 1 year of age, advanced polymerase chain reaction methods and microbial plating techniques are used in-house or sent to certified third-party labs for verification. The chemical testing regimen goes even deeper. In addition to previously mentioned standards such as moisture and HMF, tests are conducted to confirm that no contaminants have been introduced during packaging. This includes screenings for bisphenol A in plastic containers, phthalates, heavy metals like lead or arsenic, and residues from cleaning agents. Food-grade lubricants used in machinery are also tightly controlled to prevent incidental contact, and testing verifies their absence in finished products. Random bottles are sometimes subject to full shelf life simulation testing, where accelerated aging is used to project how the honey will behave under various conditions over time. Now it's time to go into the regulatory labeling and export compliance procedures, a crucial and often complex step for companies that ship honey across borders. Labeling is governed by a mixture of national food laws and international trade agreements. In the United States, for example, the Food and Drug Administration requires that honey be labeled with the common or usual name, net weight, ingredient list, the name and place of the business, and nutrition facts. Additional designations such as raw, organic, unfiltered, or wildflower must be substantiated with supply chain documentation and laboratory verification. For export to the European Union, labeling rules become even more intricate. The EU requires origin declarations if more than one country of origin is involved, meaning that a blend containing honey from, for example, Argentina and Canada must say, blend of honeys from more than one country, unless the exact percentages are broken down. Pollen analysis and isotopic testing are commonly used to verify the authenticity and origin of honey destined for the EU, and the entire production process must comply with the European Honey Directive. This includes ensuring that no heat treatment exceeds 40 degrees Celsius if the product is labeled as raw, and that no enzymatic activity is lost. The labeling department works in tandem with regulatory and export compliance officers, who maintain up-to-date databases of international standards, customs documentation, and product certifications. These certifications may include organic certificates, non-GMO verification, halal or kosher certification, fair trade documentation, and country-specific certifications of analysis. Every pallet destined for export is linked to a detailed manifest, and random audits ensure that the physical label matches its digital record in the product lifecycle database. Any discrepancy can halt a shipment and trigger a full traceability review. But up next is the specialization phase, where some facilities go beyond traditional honey and produce value-added variations to meet niche markets or changing consumer demands. This might include whipped or creamed honey, honey infused with natural flavors or botanical extracts, or honey blended with additives like royal jelly, bee pollen, or propolis. Each of these variations requires separate processing lines or batch scheduling to avoid cross-contamination and to comply with labeling laws that distinguish these products from standard filtered honey. Creamed honey, for example, requires controlled crystallization to achieve a smooth, spreadable texture. After filtration and homogenization, the honey is seeded with a small amount of finely crystallized honey and slowly stirred under cool temperatures in a creaming tank. This controlled environment allows microcrystals to form uniformly, resulting in a product that remains spreadable even when stored at room temperature. The tanks used in this process are jacketed with cooling fluid and fitted with slow-turning paddles that prevent the formation of large crystals. Flavored honey follows a different path. Natural flavor compounds such as cinnamon, ginger, vanilla, lemon, or even chili are emulsified into a small portion of honey before being slowly blended into the main batch. This ensures even distribution and prevents hotspots of flavor. Each additive must be food safe, approved by regulatory bodies, and tested for interaction with honey's enzymes and acidity. In some cases, additional filtration or viscosity adjustment is needed to maintain the same flow behavior in the bottling equipment. These specialty honeys are typically packaged in smaller volumes and targeted toward gourmet or health-conscious consumers.